Thank you. Compute control machining, or CNC, comes from computer numerical control. It's actually like CNC, what we usually call as CNC, are all the machines, because all the machines are computer numerical control machines. Like 3D printers are computer control numerical control, like laser cuts are computer numerical control. But it's a terminology that is widely used usually for like what we know as CNC milling or CNC cutting. We always need to state the last part of the acronym to actually specify. If not, it's CNC, laser cutter, CNC, 3D printer. You want to establish like that. We always start with like all the data fabrication process. We design something, we save it, we put it into the machine, and in that step, we produce what is called the CAM file, the machine outputs or physical object. This part is, let's hide these float emitting controls, is computer-aided machining, is part of the subtractive methodology. And in the subtractive methodology, you have already seen like laser cut, engraving, vinyl cutter, and now is CNC milling. You already saw this methodology with the small milling machines for making the PCBs. You already are milling. What you are doing is what is called a 2.2D or 2.5D type of milling. In CNC milling, we have like different approaches, depends basically on the machine that you have. But in a standard 3-axis machine, CNC machine, is one of the widest machines that you can find all over the world. It's the easiest machine to find everywhere. Like, it doesn't matter the country, location, you can find CNC machines in the middle of the jungle because it's a machinery that has been widely extended for like medium to large size fabrication. So it's widely used in like wood shops, carpentries, like metal shops, etc. Because it's a machine that is really powerful, is more or less easy to use, and can cut and produce really good professional results with a little bit of skills. There are 3-axis machine, 4-axis machine, 5-axis machine, and more. Like I think there have until 7 or 9-axis CNC machine centers. When it comes up to more than 5-axis, they are not called anymore CNC milling machines, they are called machining centers because they are like enclosed, they are big, huge machines that actually, for just to give you an idea of the average, a CNC machining center can easily measure the size of a car, but only output something that is in the volume of a 3D printer because they need a lot of mechanical parts around it to build, to make the objects. It's a subtractive procedure. Basically, if we want to have the simplified approach, imagine a big driller attached to a machine. Basically, we are cutting with a rotating cutter knife. That is the milling bit. There are different types of terminologies for that, but it's a milling bit, and in the case you will use what is called end mills. It's really flat or round type of end mills, but that's only one of the little part of the family of milling bits. Basically, we take our driller and we start cutting the material by making small cuts at really, really high speed until we get the desired cut. With this technology, we can produce really simple and 2D cuts, also something that you could find in, like, for example, laser cut, but with thicker materials, or you can produce 3D models in a kind of complex and really smooth finishes. Compared to a 3D printer, for example, you will say, okay, why will you use a CNC milling machine compared to a 3D printer? First, the materials that you can process with the machine are completely different. For example, nowadays you can 3D print stainless steel or aluminum, but the accuracy and surface finish of the models that you produce with a 3D printer of so are rough. They don't have really high tolerances. Actually, it's widely used, for example, in the aerospatial industry to produce like 3D printed stainless steel parts or aluminum parts, but then those parts are three-dimensional milled with a CNC. to get the tolerance that you require, because the output models of these 3D printers are not that accurate as the outputs that you can produce with a CNC milling machine. For example, engines, like car engines, are made by foundry of aluminum, the big block, the massive block of aluminum, and then they are milled or lathe with CNC machine to actually get the tolerance that you need for the inside mechanical parts. It's a really powerful machine, and it's quite easy to use. Could be really dangerous if you don't use it properly. I know, I'm not gonna lie, I know people that had accidents, like they're missing fingers easily. It's something that you can easily lose with a machine like so. Worst case scenario, you can lose a hand, etc. But say that, we never had an accident, just because we are really cautious. Why there are machines that in general that are more dangerous than other machines? First, most of the CNCs, not the machining centers, CNCs, what we know as 3-axis CNCs, are open machines. That means you can actually enter the working area meanwhile the machine is working. Think on the laser cuts that you have used before. The laser cut has a cover that you are not allowed to put your hand or your head in the cutting part meanwhile the machine is working. And if you open the cover, the machine automatically shuts down. You have used a big laser cutter, for example, the big laser cutter, it could be dangerous because it's an open machine. That's why, for example, you have like, I don't know if they explain you, but they have some like laser guides on the outside of the machine. So if you get too close, the machine stops also. Maybe they didn't experience that, but they have some sensors to actually recognize if you are close to the machine. In case of these milling machines, they usually don't have that many of these safety features because at the same time as they are more powerful and they are one of the most industrial machines, they are meant to be used in industrial environments where safety is a must and is already enforced via another house. It doesn't need enforcement on the machine mechanism. You are using by protocols on the operators of the machine. You can do a lot of things, and actually you are constrained basically on the complexity of the cuts you want to produce. You can produce, for example, on the left, we have seen that this is a 3-dimensional milling of a guitar. Actually, like, is widely used to produce guitars, like electric guitars, molds, etc. In this case, you are only cutting one side or 1.5 sides of the guitar. In this case, with a 3-axis machine, you will need to flip your cut when you have finished one side and cut the other side. So that means you have a semi-manual process involved, and it depends on how accurate and the care you take while turning over your part, you will get better or worse results. Or you can produce larger parts. For example, the right canoe is made by like making a big puzzle of parts. We will see later what this kind of big puzzles. It's assembly of 2D parts or 2.5D parts, the same as you did with creating, for example, a waffle in the laser cut, but what the difference will be that you are using thicker and stronger materials. Yes? Yes, because depends, let's go a little bit on, but depends on the end mill, not all the end mills or milling bits can be straight. Some of them have shape and you can have underneath cuts if you use a specialized tool. So in that case, you can reach a little further than the vertical projection. It's used to produce durable and strong parts. I will say that is one of the biggest difference between other digital fabrication technologies is the materials that you can input. You are constrained basically to the power of the motors of your machine, but not only that, but also on the milling bit. So milling bits, they exist in multiple and different materials and different coatings to have like stronger results. For example, you can find milling bits is the cutting part of the tool that are made of high-speed steel. That is, like, say, reinforced steel. Then you have carbide, carbon reinforced steel. That one, of course, is slightly stronger. Then, for example, to give you an approach, the ones that you have been used to cut your PCBs are carbide, aluminum, titanium, silver coated. That means is reinforced steel with an aluminum and titanium coating. What is the coating for? Just to make them strong while cutting, for example, other metals like copper. Even copper, you are cutting in a really, really thin layer, 0.1 millimeter, is still copper. Copper is strong. So in order to don't break your end mill, you are using a reinforced micro end mill. You have even diamond coated end mills. Of course, those ones are quite expensive, but it's to cut like high strength ceramics or like composite boards. For example, these are like, actually it's a bicycle crank. And in this case, you say, hey, but I cannot take my crank out. For example, this could be for making the mold of a final crank. So actually, when you want to produce most of your plastic parts that we have everywhere on our daily life, all the plastic parts are being made by injection molding, like 90% of them, or a rotary mold. That mold usually is made of stainless steel or aluminum, depends on the amount of objects that you want to manufacture. In order to have like strong molds that last a lot and can resist like 100,000 units of injection, they are made in steel. How you manufacture that with enough tolerances? You do it with a CNC milling machine. Or for example, this right piece of furniture is like something that is easily approachable that is made out of plywood. Plywood is a really good construction material and you can use for making houses or making furniture. Actually, like most of the furniture that you find, or like all the furniture that is inside the lab is made out of plywood because it's a material that is super easy to cut. It cuts like butter on the machine and is strong enough to make like resilient furniture. There are different techniques of while you want to produce your objects on the CNC. The standard one is, for example, use the same techniques as the laser cut. Have a 2D stack or a puzzle of pieces that are 2D cutted, and you then later assemble them. For example, the black chair is just stacked parts glued together. I don't know if they use bolts or screws, but could be also glued. In this case, you take the standard same approach as the laser cut, but you use thicker material. Remember that in the laser cut, you have a limit on the thickness of material you can use. That is basically depends on the power and the focus beam of your laser. Usually that maximum material is not specific, it's based on the like edge quality that you want to have. But let's state that for a more or less good and accurate cut of a laser cut, you never go higher than 8 millimeters, 10 millimeters as much on thickness of the material. In the CNC, you have the constraint of the maximum thickness of material is not determined by the technique, it's determined by the machine. Some machine, they have like a higher bridge that is more or less this distance. And this will determine the amount of materials that you can cut. The mill bit can cut like whatever size. There are like, depends on the collisions that you have on the machine, not on the technique itself. For example, as we can use other materials more than, for example, wood, cardboard, acrylic, you can use metals to cut it. You can start changing a little bit how your mindset works and produce some different cuts. For example, this table, this seems aluminum, I don't know. This could be easily produced by making 2D cuts. Metal bends. So if you use thin enough material, you can produce this line cut and this circle cut, and then just twist and bend the material. So actually you can expand the material. The same as you could do with flexible models on cardboard on the laser cut, but you can do it with metal. One of the biggest difference between CNC milling and laser cut is the depth of cut. In a laser cut, it's really difficult to control the total depth of material that you are cutting. When we do an engraving, this kind of superficial scratching or burning that we do with the laser cut, imagine that here I put the laser and I engrave my picture, you are cutting material away. But it's difficult to control the total amount of material that you are eating or destroying. In a CNC mill, sorry, you can control exactly how much you go inside the material, the total depth. So if you have, for example, this is a 20 millimeter board, you can exactly cut 15 millimeters and leave just 5 millimeters of leftover material. Why? For example, you could use this technique not only to have like the design that you want, but to make wood flexible. A 20 millimeter thick piece of wood is not flexible. A 5mm piece of wood is flexible. So you can transform, for example, a thick piece of wood in a flexible piece of wood with just some constraint. So when you bend the design, these little notches, they will touch to each other and constrain the amount of rotation or bending that your model will have. These are, for example, some examples of 3D mill part. And actually one of the largest objects, not the largest object in the world, but one of the largest objects was the house that this school did in 2010 in the Solar Decathlon. Solar Decathlon is a European, well, it's international architecture competition for eco-housing. And actually this house was built exactly where you are right now. They use the whole space to cut with just one small machine, small, like standard size, the one that you will use, exactly the same machine, and they basically cut parts in a big puzzle for during 3 months, and they assemble the house here, and then they disassemble it out. Is this house. Actually, you have the model just in front of you. So as you see, it's 2010, super high quality picture. So this full house was completely made with the CNC. Some parts were also laser cutted with a big multicam that you used 2-3 weeks ago. And it's a whole digital fabrication house. And for example, here you can see this is the main hall with just all the ribs. So in this case, what is the limit and constraint to produce large objects? Basically, on how small you can make your parts. What is the max size of your parts? Basically, is the max size of your machine. So based on that, I know we don't see really well on the picture, but basically this is one continuous part until here, and then we have another continuous part. So we have small ribs that they later be assembled all together in a giant puzzle. This is the school, meanwhile assembling it, and this was the interior. Pretty similar to this, for example, is the WikiHouse project that is actually open source project onto like the housing to produce CNC ready house designs. They're quite nice, and they have like a lot of documentation and really nice IKEA drawings. So basically they push for like self-fabricating your own house, and they have like all the instructionals and guides on how to do it. Basically, the only equipment that you need is like two or three people to assemble the parts just based on the weight of the material, wood, and a CNC to build your whole house. This is more examples of the Eco House. Other projects that, for example, I want to show you. We have the Fab5 that is actually it's a quite interesting project. This is a project of the CBA and MET, as far as I remember. It's from them. That is to make, yes? Okay. That is to make antennas, really low cost antennas into like development countries. So for example, Afghanistan is known as not a really high electrified and technological countries right now. But then you have like some villages that are really uncommunicated. So they got the idea of using all routers or modem, like Wi-Fi models, and enable and strengthen the signal of those like all routers with a wire mesh antenna. That is a kind of DIY antenna to actually enable longer range communications. In order to produce this, they embedded into design that all the frame of the antenna, to keep antennas are quite sensible on the shape and the geometry, to have accurate control on how the antenna is being made, and to keep control on the signal, the antenna should be CNC fabricated. Why CNC and not laser cutted? You see, it's antenna, it doesn't need to be that strong, it's something that is more or less light. Why? Because they designed it completely to be CNC. Why? Because the CNC machines are easy to find everywhere, way easier than a laser cut. For example, a cheap, really cheap CNC machine, like not super high technological, like not the best brand, could be easily found in like full size. It means when we call a full size CNC is 2.5 meters by 1.2 meters, it's quite huge, by around like 10K. A laser cutter of that size can easily cost 80,000 euros. like it's almost 8 times more expensive. And you're still constrained that it's a machine that is 8 times more expensive, but and still cannot cut really strong materials or really thick materials. So actually it's like cost benefit of getting machines like that is way easier and better to get a CNC because allows you to cut more and have more possible outcomes up to the price of the machine for the same price. So in this case, they analyzed and they found like in a town in Afghanistan, they had CNC. So actually they designed all the parts to be produced locally instead of shipped. That is also something that don't know if you know about the project 5 City, but you don't send things, you don't just send bits or designs through the internet and they can produce it locally. Actually, that's one of the best things. So, like the fourth industrial revolution, stop sending things all over the world. So actually they embedded into the design and they designed the whole system to be easy fabricated all around the world. And what is the easy machine that you can find all over the world? It's always a CNC. So basically they make the whole design in easy to cut with a standard material like that is more or less a 15 millimeter or 12 millimeter thickness of wood. That is something that you can find everywhere to cut in a milling machine. Not only big, but also small. Something that usually Mac lovers will love this moment. Mac, Apple products usually use aluminum for the whole casing of their products. And it's a good example because they have like YouTube documentations that you can watch. Your laptops, and depends on your phone, if it's an aluminum phone, not only Samsung also does, they are CNC milled. Welcome. So basically they put the aluminum in a foundry, they get the big rough like product, and they then like mill in the inside parts of your computer. So your computer is milled also. This happens with almost all the aluminum parts. And you can do it with a really, really accurate and small finishing. Basically, this is determined by the size of the end mill, how accurate you want to do your cuts. For example, this is a small product showdown that is a SD card holder for expanding your memory on your computer. You can cut aluminum, yes, but you will cut, when prototyping your design, automatically the aluminum part, never. And this is when we are reaching, they already got the big three, that is 3D printing, laser cut, and CNC. Is the big three technologies of digital fabrication. And you never use just one of them. You combine them when you prototype. You use what technique for what it does the best. CNC usually is slightly slower and it's more time to set up the values and parameters to get a good cut. But on the other hand, you are getting a really good and accurate cut. Okay, and you can cut really expensive materials. So it's the first time you want to produce your model of your SD card holder. You want to find the final product will be in aluminum. Would you want to cut aluminum the first shot? Never. Why? You need at least 2 hours to set up the files. It's a complex cut, and you're using expensive material. Do you want to first test the geometries, like a basic geometry test? Okay, use your 3D printer. It will be easy, fast, and good to make the setup on modeling, on tolerances. So you first, for example, this is about prototyping stages. You first 3D print your prototype. It's cheap, easy, and you can do it really fast. And it's really comfortable to do it. So you print your model until you get your good tolerances. Of course, the tolerance between a 3D print part and a CNC part are slightly different, but it's something that you can accommodate through the prototyping process. When you have tested your tolerances, you still need to do your electronics. For that part, you can use the traditional chemical path of electronics, or you can produce your PCB circuits with a small milling machine. When the electronics fits already your 3D printed prototype, and you are enabled inside all the electronics, and everything seems to fit, now, for example, let's try to jump to the beta state of the product. Now is the time to change to the final materials. And this is the final stage of prototyping when you actually produce the final part in aluminum. And you do it by adjusting the final tolerances of your product. So this is, for example, some prototyping steps that you take all over. And you mix techniques. For example, this PCB, in case you want to use a flexible PCB or a really specific PCB, you can use a laser fiber machine to actually engrave the PCB because you are getting really small circuitries. So you never just use one technique for producing your object. You always mix the techniques and you change depends on the prototype stage that you are in. For example, something that you will get, and I will say is mandatory for this week, and for the challenge is you never cut your design directly on the CNC. You scale it down 1 to 5 or 1 to 10, and you cut it in the laser cut. If you can assemble your model in the laser cut with just thinner materials, just scaling down the materials, your model will be probably easily assembled in the CNC. Happens a lot. We see every year, more or less half of your models fail on the CNC. Why? You didn't think of the assembly sequence. So you try to assemble one part, you try to assemble the other directional part, and it doesn't fit because it's impossible to assemble. Everything in the computer, you can easily assemble. Objects can go through in the computer. In the real life, no. Also, we have tolerances, like, or things that, for example, we have seen a lot that chairs, that they look really cool in the computer, and when you want to sit, the table just bends on the back because it's not stable. The only easy way to test, for example, a small model of a chair is make the, it's a really silly thing, but is make the laser cut chair in small and put your phone. More or less is the same scale and weight of a human on a normal chair. So when you always want to test something, a new design, you never go to the final material. First, let's go a little bit on another example. For example, the Metropol Parasol that is in Sevilla is a full CNC cutted structure that is huge. This is massive. Of course, it's not cut at once, it's cut into several small parts to actually produce this. So this is about the step of prototyping. Why you want to go onto the laser cut before the CNC? Let's just speak on the money right now. This is a composite material. This is a final product. This is a kid's game that is made of a composite panel that is called Alubond. Alubond is aluminum, a foam core, and aluminum. So it's strong, it's water resistant, it's really light, and is easy to move and easy and really good to cut. It has like the final end of the final quality of an end product. More or less to give you the cost wise, a full size of Alubond can cost easily 300 euros. Do you want to cut your design completely, spend like 3 hours, that is more or less what it takes to cut Alubond a full size on the CNC, spend 3 hours, 300 euros, try to assemble your parts and magically nothing fits because the tolerance is wrong or because your design is wrong? You have already wasted your time, that is even more expensive, and the material? No, you want to do a small, fast, cheap test of geometry on the laser cut. You can use, if, for example, this material is 50 millimeters, you can scale down 10 times or 3 times and use 5 millimeter cardboard. It will get the same joinery. You don't need to modify your design or almost nothing, like a little bit of tolerance. You can use 5 millimeter cardboard. That is something that you can easily cut. You can cut the whole design in just like 10 minutes, a full board of cardboard in the laser cut because it cuts really fast. You can test that geometry can fit, everything on the design is okay. And when you have double check that your geometry and design is okay, then you can move on and cut the final product on the CNC. When we produce cuts on the CNC, we also need to embed again the nesting. That is also, we already mentioned in the laser cut, that is a technique to actually match your parts to each other to actually save amount of material. We already saw what we can use Deep Nest or Nest.io, that are some online tools, open source, to actually nest your objects. There is also Rhino Nest or Grasshopper Nest. Like all the different softwares have already alternatives to actually nesting. Why is even more important this in a CNC machine? Because you are using just more expensive material. So the less material you waste, more money you are saving. And also it's good for the environment because waste is just waste. And you can be a happy kid with your 3D model made in real life. Not only for like more professional projects, but also art projects. For example, this is a shadowing window. This is an artist that basically want to produce some like light shadow effects. Foam is a material that you cannot laser cut. Foam is a material that you cannot 3D print. The only way to process foam is by either making a custom mold and cast the foam on yourself. That is usually a nasty process that you don't want to do. Or you can take a piece of foam and mill it up to shape. Actually, like this technique is widely used also for producing like scenarios, like on theaters, cinema, like backgrounds, because you can produce large objects in a cheap way with really cheap materials like foam. And you can produce really complex three-dimensional cuts. This, for example, is a 3D cut. PCBs, yes? Sorry, this presentation is really old, I don't remember. Milling PCBs. This, we already went through it a few weeks ago. For example, I always, for the ones that are really not confident with the design and still want to test this, this is a really old tool that you still can download. It's open source. It works really bad. I have to be honest, nowadays, like compared to the new programs, this program is already like 6 years old, easily. It's called Sketcher. So basically you design a 2D sketch and the program automatically will create a waffle structures for you, and you can create a test dummy to see if your chair is stable or not. But I want to show you this because this is a 3D waffle of a chair design. Even if your model, like your program like this, can test the stability of the chair with a dummy and a small physics engine, you still want to test it in small. If you can test it even in really small, use, for example, thick cardboard and a vinyl cutter or a laser cutter. This is, for example, this is a vinyl cutter to test a small chair. And look how happy is the guy with a small chair that can put his iPhone. Then when your model fits, you can try to cut thicker materials and test again for the validity of your chair. And with that, you can, for example, test and make a lot of iterations, not only test that your geometry works, but you can produce a lot of modification your design and do really small tests to see and prototype better, because you can actually real test your chairs. And it's something that unless you are really an expert in fabrication, get to see how the 3D models really accommodates reality. It's something really different. In the computer, everything works. It's a magic world. Like we have games, we can imaginary sci-fi worlds. Computer is not reality. Your 3D models almost never are exactly the same as your final objects, unless you know exactly what you're doing and you are really get used to. So something that, for example, a curvature like this could be really comfortable in what it seems, in what it seems like the knee of the model, could be really comfortable, could be disastrous, like annoying to sit on. And it's something that takes time to get used to these kind of things. Unless you are, I'm just speaking right now of furniture, but furniture, 5 degrees change on the tilt of the back can make a huge difference of people sitting or not sitting in the chairs. For example, well, this is like a little bit of activism, but in the lab that I previously worked on, we made all the furniture of the lab. All the lab was completely made on the CNC. We had one room that is for the workshops and usually used to workshop at night. So people like get tired after work and they come to the workshops and they start to get sometimes slept in the workshops because it's a long workshop, the same as you are doing, but imagine this doing it at 10 at night. People is tired and sometimes get sleep. So actually we introduce a change. We make new chairs, but we make them like 5% tilted on the front on the seating. So actually the chair was not really stable. So people never tend to get sleep because the chair was not really comfortable. No, there are little things like that that you can introduce into designs to actually make people don't sleep on a conference. Cuts for software for design. Like this, I don't need to explain. There are millions of types, and all of them, most of them can produce directly files for CNC milling. Why? On CNC mill, we can actually embed 2D files, 2.5D files, and we can embed also 3D files. This is cool design softwares. We already went through them in the laser cut week. Let's go a little bit of why of the benefits of using, for example, a CNC. First is automation. This not only applies for CNC, but for 3D printing or like almost any digital fabrication equipment. Is meanwhile the machine is working, you can produce a lot of things. And you are, right now you have seen, for example, in 3D printer, a small 3D printed part, like, I don't know, like, okay, this little benchy is this. I don't know if you see on the camera, but this little boat takes 1.5 hours on printer. It's super annoying. It's super slow. But that doesn't mean that you need to stay in front of the machine just watching how it prints. Meanwhile, the machine is working, you can go take a coffee or make your next boat design. So one of the things of using this fabrication equipment is automation. Accuracy. I like a lot this diagram. Machines are really accurate. And I really hate that you say, oh, the machine went crazy. It's not doing what I told it to do. No, you didn't set up the machine properly. First, like, I will never trust you, never. The machine does exactly what you tell the machine to do. It's following just a set of instructions. If it's not doing properly, it's because you have set up wrongly the machine, either on the file, either on the mechanical or hardware part. You didn't attach your end mill properly, you didn't tighten the collet, you didn't put your material properly, you forget one of the steps of like making the origin, etc. There is millions of things that you can go, and it's about the workflow of the machine. So machine always is really has high repeatability and high accuracy. Just to give you an idea, the worst accurate machine in the lab right now is accurate to 0.5 millimeters. It's not even half, it's lower than half millimeter accurate. So it's way more accurate than you, first. Second, it can repeat things with an accuracy of 0.1 millimeter. Repeatability is how accurate or repetitive a machine can produce the same cuts all over, like 1,000 times, with the difference. It means if we produce 1,000 objects and we produce cuts of 1,000 lines, all of them will be exactly the same up to a tolerance of 0.1 millimeter. That is 1/10 of a millimeter. That is really small accuracy. That means the machine is repeating all over again and again and again the same cut with almost the same results. For example, just as curiosity, you know why products fail, like standard, like household products, or like, for example, Macs. Sometimes you buy a product and it's defective. Because it's about that, accuracy and repeatability. Imagine that you are cutting 1 million Macs, like MacBook Pros, of aluminum. You are using a milling bit to cut the holes for the electronics. The milling bit gets wasted on the use. Like, it's an end mill and needs to be refurbished or replaced to a new tool to produce the same exactly amount of cuts, because it's the same with a cutter knife, a cooking knife. A cooking knife you cannot use for like 50 years and still get the same cuts. You need to get it sharpened. Happen the same with the tooling. And this is about manufacturers' workflows and when they change the tools. So if they just change the milling bit and the first unit produced to make the MacBook, the first one is going to be perfect. Perfect shiny cut. It got a super nice cutting milling bit. On the unit 10,000, the milling bit has already got a little bit unsharpened. It's not producing exactly the same amount of cuts and get that good and sharp cuts. So the mill bit needs to be replaced. The 10,000 unit is slightly worse than the first unit of the same batch, for sure. And this is only about milling. Like there are a lot of like fabrication process involved into that like production line. So what happened is some manufacturers, they extend that margin a little bit further, and some of them, they take it closer. That's why I'm talking about manufacturing in industry. So manufacturers, they charge really high cost for manufacture something, and some of them, they charge really low cost for manufacturing the same product. Why? Because it's how much control they have over the like chain production line and replacing the components that need to be replaced on the production line. It's not the same producing with the same tool 1,000 objects than producing 100,000 objects. Of course, you are saving money, but you are saving money in some parts of the product. And that is where your product needs to be, has slightly better or worse quality. So not always all the price we pay for products is on the manufacturing, could also be like brand, these kind of things, but sometimes yes. Depends a lot on the process that you are doing. Sorry, sometimes it gets too lost in these kind of things. So this is about repeatability. So changing the machine is doing exactly the same cut with a small lighting margin of difference that is about replacing the materials. To give you an idea, for example, here we are teaching you how to use a CNC milling machine. We have tools, and those tools need to be replaced. You are cutting wood, and usually your designs are not the best. So we change, usually in a wood shop, like professional wood shop, something that produce something that they sell, they change the milling bit each 20 to 50 panels of wood. Here, as the cuts you are producing, they don't need to be the best out of the market. And usually what fails is not the cut, it's your design. We change the milling bit every 100 to 120 panels. Why? Because we don't need to get that sharpened cut, because we know that the model will not fail exactly on the cut, will fail on the design. So it happens the same. Imagine that we are making a little stool. Traditionally, a woodworker that produces carpentry for his 50 years of history can produce exactly the same stool all over with really small differences. And it will do exactly the same stool, but will never get exactly accurate to the plans of the stool. It's producing, has like a traditional expert will produce really accurate cuts and similar stools, but never exactly perfect. There is always the human factor in the fabrication. For example, case B could be someone that is a little bit skilled and knows how to use like traditional hand tools and is trying to produce a stool. The first tool, okay, it's not perfect. The second stool, oh, it's perfect. It got to the point. It's getting good. The third stool, okay, fail again. Doesn't have the expertise of the traditional woodworker. This is the machine making exactly the file that you told it to do with a little bits of change and difference, because the material changed a little bit, or the end mill gets a little bit wasted, or you didn't set up the material exactly the same. There's always the human factor. And then we have the non-skilled person that actually makes tools that cannot even be seated on. Flexibility. This I will say that is one of the best factors in this case. That is about amount of equipment that you need to do. Have you ever entered a traditional wood shop? It's full of tools, all over. You can replace, not all, but a lot of those tools just with one equipment. Being that said, for example, you want to produce a circle, a flat circle out of a piece of wood, traditionally in a wood shop. You need a vertical bandsaw, then you need a trimmer, then you need a sanding machine, and between each process, not only you need to do it manually yourself, but you need to move to different locations of your lab. That means you need a lot of handwork. You can produce the same outcomes with just a CNC milling machine, just placing the material once, and let the machine do the process, the three processes at once. one after each other in an automatic way. So not only you can reduce the total footprint of your lab by reducing the amount of equipment, but you can automatize a lot of that process with just a single machine. So actually, the equipment by per se is a little bit more expensive, but you can always reduce the cost down because you need less space, you need less machines, and you are automatizing a lot of the job. Machines takes no breaks, and humans does. Actually, the best you can do is try to automatize and do the most of the things with the machine as you can. So maybe the cut doesn't take just 1 hour. For example, something that a lot of people make the mistake is, I want to cut fast and I want to produce my piece fast. Okay, I spend 1 hour in the machine and the machine has finished, yes, but then you need to spend like 1 hour sanding. If you spend 1.5 hours on the machine because you take a little bit more time to set out your files, or you just change to a second process, you can get automatically the file sanded on the machine. So basically you are saving half an hour. So sometimes it's better to spend a little bit more time on the machine to get better cuts than try to save time on the machine, because time on the machine is something that meanwhile you can do other things. You can prepare the next file. Also, we need to be careful. I just imagine myself or yourself trying to make 50 chairs a day. On the chair number 40, I'm super tired. I'm using like electric equipment, rotary blades. I can easily get a cut. Actually, a cut. So basically, humans get tired, and you can produce like risk, and you can get cut easily when you are tired. The machine doesn't care if it cuts like 24 hours in a row or 60 hours in a row. The machine will get exactly the same cuts. Not only is it better for accuracy, but it's also way safer. Even so, never use a machine when you are tired. Really important. Yes? So they just ask if it's, let me see if it's difficult to hear. They just ask if it's safe when, for example, if you are cutting metal with a machine, if it produces sparks or so. Usually, you should not produce sparks first. Sometimes happen that some pieces of material can ignite. It doesn't need to be metal. I have seen wood turning out of fire. I have seen a machine on fire, a full machine. This is because about bad setting on the quality, on bad settings of the machine on the cut. It's something that you should always avoid. There are mechanisms when you want to cut like high strength materials to reduce that risk. But if you are cutting properly, you should not get sparks of any kind. What you see sparks, maybe on some machines or some pictures, they were not CNC milling machines, they were plasma cutters. They cut with plasma. That are meant to produce sparks, but they have different mechanisms. For example, they have a water bed to actually avoid fire, etc., etc. But milling machine producing sparks is something really wrong happening there. Types of CNC machines. We have the most traditional and widely extended 3-axis machine, X, Y, and Z. Really similar to a laser cut or a 3D printer. These ones, they can produce 3-dimensional surface with just one side of the machine. They come in small packages, really small, as you have seen for producing your PCB files, or they can be in large size. For example, this is a full size extended. This is more or less 2.5, well, it depends on the machine, but it's 2.44 to 1.22. Or giant one. They are really huge one. Actually, this building could be one if it was like not that old. But here we have, on the back, we have a bridge. Usually these kind of machines, they usually use the main building structure as the frame of the machine. So for example, I don't know where this picture is, but the ETH Zurich, they basically build the machine, the frame of the machine, and then they make the building around the machine. Usually those buildings are built the opposite. This is for producing usually large size molds, not for producing final outcomes. It's for producing massive molds for like being reused and reused. Even with the small size machines, for example, depends on the culture, but in United States, it's really common. Like there is a lot of like garage culture, and there is quite common to see CNC machines in a garage. And actually, they have the same size of a car, so it's really easy to match. And even with these small size machines, you can produce really large objects. For example, this is a fin. I think it's the fin of a boat. For example, this, as I said before, like Apple products, most of them are machine. Just for example, this mouse, wood mill mouse, is also machine. Of course, machining this is not easy. It's not something that you get on your first cut. Like I would say that even machining this, like it will be quite difficult even for me to produce this mouse. We have 4-axis machine. Usually, the 4-axis machine is to introduce a rotating tool. And this is usually it's not a machine that is 4-axis per se, it's a 3-axis machine with an extra add-on. They basically embed a 4th motor, usually in the middle of the bed, that is meant to clamp something with some like pressure clamps and hold your objects and rotate meanwhile you're cutting. This has limited applications and is widely used for 3-dimensional engraving, for creating wood legs. It's kind of approach of transforming a 3-axis CNC into a semi-automated lathe. Lathe is the rotating machines that they produce cylindrical objects. It's funny, but this accessory is also sold for laser cutters. For example, like a lot of the glass or like glass containers that are like laser engraved, how you engrave something that is cylindrical in a laser cut. You need to rotate to always keep the focus on the tool. So you rotate the bottom. It's funny because when you embed this accessory in a laser cutter, it's not anymore a 2D laser cutter, it's a 3-axis laser cutter because you are missing 1 axis. It's not a 4, it's a 3. For example, you can produce pens or, for example, this kind of wood containers. This could be milled, and then this is also engraved with a laser cutter with a 3-axis add-on. 5-axis milling. Usually, unless you have a machining center, you use a robotic arm for milling. We already saw in the robotic arm class that a robotic arm can do almost everything. The point is we take basically the same motor as you have using a like CNC machine, just attaching the motor. If you're curious about it, for example, for the big hookah that we have on the back, we have a big CNC motor that we just took from an old machine and we just mounted in the robot. For example, this is a quiz question. How you can produce this like mold, I think it's foam mold of this car. What machine you need? Come on. Okay, we see 5-axis, 3-axis, 5, 4. All of you are right. Depends on the amount of human labor that you want to add. So the basic shape of this car before was a block of foam. With a 3-axis machine, you can cut the top and more or less until half of it. You can only see the top projection of the car. You can only cut it. How we cut the side? We use guides, and we don't have here, but for example, we can use these guides and a rig to actually rotate our foam and produce the other side of the cut. And then when we have finished this, the top and the side, we can rotate in the other direction and produce the other cut of the side. So we have a quite annoying and lot of manual labor process. With a 4-axis machine, what we can do is just clamp on this axis and clamp on the other axis and just rotate. Can I? Whoop. And just we can clap here and here and just rotate the mold automatically to cut the top, the side, the bottom, and the other side. We can automatize a lot the job. With a 5-axis or 6 or 7-axis machine, what we can do is just cut all the directions, but we need to always leave a little bit on the bottom of the car to always hold the piecing part. So it's not about that the machine cannot produce the job. but is less or more automatized. Obviously, it takes less time to produce this with a 6-axis milling machining center than manually, yes. But the complexity of controlling a 6-7-axis machining center is huge. It's not something that you do as easy as a 3-axis machine. Just to give you an idea, a CNC operator, a professional one, is a paid job that basically his job is just to know how to set up the files and set up the properties of cutting and knowing the machine. So CNC operators usually they have training in some specific machines and they know how to operate only the machines. And it's a paid job that is huge. Like it's a 5 to 7K paid job. It's a really good salary. And his only job is how to set up the file and the machine properly to basically don't cut the machine also. Because the machine, as it can cut in any direction, can also cut itself. I have seen, not kidding, I have seen 3-axis machine not only cutting the material, I will explain you with a picture. We have it. Okay, let's see with this picture. I have seen exactly this machine. They had 20 centimeter pieces of wood on top. I have seen this machine cutting the wood, cutting the sacrificial board that is around like 20 millimeters of MDF plus 30 millimeters of plywood. Behind that, there is aluminum profile. Cutting the aluminum profile, and reaching to cut the stainless steel of the base. Of course, this guy will never enter that lab again, but it's something that the machine can do, and it doesn't care at all. Other types of machines, and we need to speed up a little bit. Yeah. Handheld automatic CNC. This is a really curious type of CNC machines. They don't have a mainframe where they work. Usually the machines have some rails that they move on and off. These kind of machines, they don't have a structure. Basically, they have some small feet and they move. It's like, imagine a little machine moving on your material. So it's a machine that walks on your material and cuts meanwhile. This is a semi-automatic, so there is a lot of manual process involved. And it's quite curious to see this machine working because basically you put your machine on the material and depends. This one doesn't work, but other ones nowadays they work and they start cutting. Some of them, for example, they're assisted. What they have is like the new generation of this machine right now has a screen and has some patterns, like a kind of GPS. And what you do is it's guiding you on the materials. It's a semi-automatic handheld router. Parts of the CNC. And this is a terminology that applies no matter how the machine looks like. Most of the CNCs have what is called the bed of the machine, that usually is a T-slot table in general. Not all the machines have T-slots. For example, the one that you will use has T-slots, but we don't have it installed right now because we never use them. A T-slot is an aluminum profile, could be one or one continuous aluminum profile that has some T shapes on the side. Basically, it's a super good and stable aluminum surface where you can clamp your material on top. We have what is called the bridge. That is one of the most important parts, and which keeps what will determine the accuracy and strength of your machine. Usually, the stronger and the wider the bridge, stronger materials it can cut without bending. That bridge usually is made also on steel or aluminum, depends on the type of the machine. The bridge is the limiting factor on the total depth of cut of your machine. So, for example, this is a 50 millimeter bridge. A 50 millimeter bridge will only allow you to cut more or less a 40 millimeter thick material. So, if you want to cut 200 millimeters or 20 centimeters of material, you need to find a machine that has higher than 20 centimeters of bridge. Usually, it's 1/3 more of the size. That depends a lot on the mechanics on the machine. We have the steppers. Does anyone knows where the stepper name comes from? I already explained it. Someone remembers? Steppers, stepper motors. we are making control movements. So we want to control a normal DC motor rotates at really high speed, and we can control the total amount of rotations per minute, but not the total angle. Stepper motors are some kind of motors that rotate step by step. They rotate 1.8 or 0.9 degrees per rotation. So we can control how many steps we are moving. So we can control and have accurate movements and control movements. We have the spindle or the router. Could be a spindle or router. We'll see this different later. Is basically the rotating motor that usually is high speed, where the cutting knife or milling bit is attached to. And we have the cable carrier. Why we have the cable carrier explained here? You say it's just a rig of cables. You need to think that CNC machines usually use powerful motors and use a powerful spindle. So that means these cables are usually huge. And in open machines, or if this is an open machine, even if it's small, this cable carrier needs to be free all the time. The machine is really strong. And actually, if you jam the cables or it gets attached to something, they could easily break the cables on its own. And usually the spindles are like 400 volts or 240 volts, so you don't want to break these cables. You need to be always careful to don't get the cable carrier attached to anything or trap into something. For example, once I got trapped by the cable carrier, I was not paying attention and I got trapped. Basically, I broke my t-shirt. Luckily, it was only the t-shirt. I stopped the machine fast enough, but you need to be always careful about this. Types of motors of cutting. We have two. I will start with the second one. It's called the router. Some of you have here maybe the machine CNC router. You don't hear CNC spindle. CNC router for a CNC machine. Routers were the standard on the machines before. Basically, it's a type of motor that is cheaper, is easy to replace, is easy to find all over, and works based on RPM, works on revolutions. It rotates at really high speed. When I'm talking really high speed, it's around like between 15,000 to 40,000 RPM, depends on the motor. So it's a motor that rotates by speed, not by strength. It's a cheap motor and has a bad point, is we cannot control the speed with the computer. We control it manually. Basically, we have an accelerator that will rotate manually. As much process as we have automatized, the better. We can simplify our job and we have more control over the process. So that's where comes the newer generation of this kind of motor that is called spindle. It's an electronic control motor. Not only we can control the speed by the computer, but also has in general a better build quality, is stronger, has stronger bearings, and it works on torque, doesn't work on RPM. So that means it has more strength. So it has more strength, it can cut stronger materials without no problem, without no fuss. In general, what's the difference? You say, why we don't always use spindle? Because they cost easily like 3 to 4 times more than a router. For example, a basic spindle, a 2.2 kilowatt spindle costs 7,000 euros. Same amount of equivalent router costs 1,000 euros or 2,000 euros. There is a big difference in price. But with the spindle, we control the speed. That is quite important, you will see on the file making. Spindle. Actually, here, the one that we mount on the robot is a spindle. The one that we have on the newer machine is a spindle. The one that we have on the old machine is a router. And in the other building, they have router and spindle, have both. Depends on the application. For example, on the small mini machines, you have seen that you can see the RPM of the robot on the motor. Those one are spindle because we can control the speed of the motor with the computer. And some of you have tested the small CNCs that we bought for the year for the academies, that when you switch on the motor, it just has one speed. That is a router. That will be the difference, for example. That's one of the main difference between the orange milling machines and the black ones is on the price cost. The spindle cost is like for that one that is a really small motor is 500 euros just on the motor. Meanwhile, the motor of the other small milling machine is 7 euros. It's a big cost difference. Collet. This is a quite important, really important part that you will go on the hands-on really in detail, is what holds the end mill. This is basically the clamping tool that holds the end mill. It's really important that this part is clean. Imagine your hand trying to grab something. I'm trying to grab the mouse. I grab it properly. I have my fingers. If in my finger I have something, like a piece of dust, something, I cannot grab properly the phone. So I'm not making force enough, and that can lead to the end mill flying away at really high speed. So it's important that the collet is clean, first. Second, that you use the appropriate collet. We have different size of tools, like we have 1, 2, 3, 4, 6, 8, like until like 20 millimeters thick. On the end mill, you need to take the collet that matches the size of your tool. So if you use a 6 millimeter end mill, use a 6 millimeter collet. It's mandatory. And I will say this, it's quite obvious, yes, but we have inches and millimeters collet. 1/8 inch is 6.1 millimeters. It's not 6 millimeters. You say it's only 0.1 millimeter difference. Yes, 0.1 millimeter difference could make that the end mill flies away or not flies away. And it's important, it's quite important. When you are in a professional environment, you want to automatize your job a lot. And that means you need to have like a lot of end mills for different purposes. We have what is called an ATC. It's an automatic tool change. So basically it looks like a machine gun that has like a lot of end mills already mounted to the machine with the proper collets, and the machine basically comes, takes one, goes, cuts, comes back, releases, and takes another one. This is a super nice accessory, but it's an add-on that is quite expensive in general. What you said before about the sparks. For example, when you cut metal, let me hide this, or just put it here. When we cut, we produce heat. We are not doing the same process as the laser cut, that we are not burning, but basically we are cutting by friction. We are producing cutting knives. It will be the same as when you are sanding something, it produces heat. We are doing this on a really small scale and at a really high speed. So when we cut wood, we produce heat also. If you don't cut properly, the wood and a metal, hot metal, what happened? A fire. That is because your settings were not properly adjusted. What happened when you cut metal with metal and everything gets really hot? It melts together, it bonds. That not only is really bad for the machine because can lead to a motor breakage, etc., but there are ways to avoid that. First is on the settings. If you use the proper settings to cut the proper values, you can cut aluminum, for example, without cooling. You can cut steel without cooling at all, just using proper values. You have a really small margin to cut. If you get above that margin, you have a failure. So a good way to avoid that is, for example, use lubing. Usually automatic lubing is only in closed machines. Why? Imagine that you have like some jets of water or lubricant or oil throwing with a lot of pressure. Basically, it's like a shower of different mixture of liquids cooling down your cut. If you have this in an open machine, the whole lab becomes a swimming pool in a few seconds. So usually these kind of machines are closed. They have this shape. They have this shape. Why? Because they have some doors, they have some water jets or oil jets or cooling jets, and basically they throw it on the material that you are cutting. Usually this is meant for metals, and they have a recirculation circuit where they clean the oil or the material that you are throwing, and they pump it again. So usually it's in this kind of machines that there are machining centers that is basically as a CNC button close with water, air cooling, etc. Let's hide this. So usually the automatic lubing is just in machining centers. In open setups, we can do what is called the manual lubing. For example, cutting aluminum, even with the proper setting, sometimes you're cutting for long times, the aluminum gets quite hot. You want to avoid that the metal gets quite hot, and you want to soften as much as possible. So what you can do is, meanwhile the machine is cutting, spray a little bit of lubricant or cutting oil on your material to help on the cut. Not mainly to cool down, but this is widely done to extend the tool life length. It means the total amount of cuts that your tool can produce. So if you don't use cutting oil, your end mill can last only like 2 hours of cut. If you use cutting oil, for example, you can extend it to 3-4 hours, just to extend the tool life length. And here we come with one of the most important things of the CNC, is how to choose your tool. Your tool is the only part that is touching your machine. So, guide to CNC mills. We have millions of types of milling bits. Actually, let me 1 second. This is an end mill catalog. It's like a Bible. And basically, you come and you say, okay, I want to cut aluminum, this type, I want to cut this depth, and you come with charts or which tool to use for each application. Of course, you don't need to know everything, and I don't know, I think that in my life, I have only used like, in total, more or less, like 50 types of different end mills. A lot of them, they can be used for multiple applications. You don't need to get crazy, but there are millions of types of end mills for different geometries, different materials, different cuts, different outcomes. So choosing your end mill is quite important. Well, if you want to check it later. So CNC routers or CNC machines need mills. We have, and this is about end mills, we have 4 big families. This picture is a little bit confusing because the end mills are right now upside down. Usually you hold here, you clamp here, and this is the cutting part. So there are straight end mills. There are upcut end mills. What is an upcut end mill? When we cut, the machine always rotates clockwise. All the tools always rotate clockwise, okay? Always. When I say always, there are some specific machines that, of course, they rotate counterclockwise. But most of the machines that you will find in your life, they rotate clockwise. So if you rotate clockwise, when you cut, the chip is the material that is you have cut it, is coming up in this direction. So you are pushing it up, out of the material. We have down cutters. The chip, you are pushing it down. And we have compression cutters. This part of the end mill is pushing the material up, and this part of the end mill is pushing the material down. You can see that here we have a difference in the geometry. There are these big 4 families. Each one has different applications, and you use in different case scenarios. Straight is not either pushing up or down. It's not doing anything. Just letting the material accumulate, and naturally it will go up, but it's not pushing it. Just to give you an idea, a straight end mill, more or less, is a 15 euros. And Now, depends on the country. This changes a lot. For example, in Europe, it's slightly different. An upcut end mill costs 20 euros. A straight end mill costs 30 euros. A down cutter end mill costs 40 euros. A compression cutter costs 100 euros. This is the most standard one in CNC machining, and it's the one that you will find everywhere. Why? It's the one that is easiest to produce, easy to manufacture, and is widely employed to cut really strong materials. For example, you're cutting stainless steel, you're cutting aluminum, you're cutting carbon fiber, you're cutting a composite. It's all around, it's good working, works more or less in all the situations, and can do all the kind of jobs. It's a really generalistic tool and works well in all the situations. A straight cutter. This one, the up cutter, also is one of the fastest one, as is taking all the material out really fast. We can go faster than the other types. Down cutter is doing the opposite, is pushing the material down. So first rule, down cutter cannot make holes, cannot do vertical plunges. Why? If you are cutting but you are pressing the material, what happened? Basically explosion, because the material has no way to escape. You are pushing and making friction. In case of wood, it's automatically a fire. In case of metal, it's an explosion, because the material cannot go anywhere else. Even so, if it cannot make holes, it's a really good tool. When we are cutting, we are making a lot of force on the material. The material tends to move. When we are pushing down, the end mill helps to hold the material in place. So it's a slower cut end mill, but in general is easier to use, but it's one of the slowest one to cut. In case of plywood, it's a really good end mill. Or in case of wood, especially natural woods, cuts really well, it's soft, it's not the fastest one, but it's good for learning. A straight one is not pushing up or down. It's a general approach kind of end mill. It's really good for plastics, for example. And we have compression. Compression is a mix of up and down. So it's taking the top layer and the bottom layer compress all to each other. Why? Why this is important? This is a end mill for cutting only composite materials. When we, well, more than composites, double layer materials. Hide, floating, control, we annotate, clear all drawings, yeah. Okay, for example, this is wood, plywood, this is a composite material. Plywood, for example, if you are pushing up with the up cutter, the top layer breaks. It's easy to break it. If you are pushing down with a down cutter, the bottom layer will break. What happened? We have a bed on the machine, so the material cannot break as easily. With a compression, what we are doing is we are pressing the top layer and the bottom layer, so we are getting the best cut. What happened? It's a end mill that you need to use for the thickness that you need to use. So what does that mean? So the change of the geometry needs to be in the middle of your material. So if you are cutting 20 millimeters of wood, you need to have an end mill compression that is 10, 10. If you change your thickness, for example, you are cutting only this, you are cutting this thickness of wood, this end mill doesn't work anymore. You need to change to an end mill that the geometry changes here. So you need one specific end mill for each thickness of material. That is something that makes it not only more expensive, but you need a big tool library to cut. And if you take into account that these ones are the most expensive ones, that increments a lot the cost. Drills are not end mills. First rule, you don't use the one that you use in the hand driller on the machine. First, the geometry is completely different. Second, the material is completely different. This is a drill bit, and this is an end mill. I need to say anything else. Look at the geometry, it's completely different. Why? The drill bit only works vertically. It's meant to be used in axial loads. The end mill can do also perpendicular to the axis load. That means the end mill can cut on the side and do also vertical movements. The drill bit, not. If you try to cut on the side with a drill bit, it will slap in half, and basically you have a metallic object rotating around like at minimum 10,000 RPMs. Basically, it's a flying bullet. You don't want to have a piece of metal rotating at 2,000 RPMs flying away. So you never use drill bits for a CNC machine. Even that the end mill can do vertical and lateral movements, we always want to reduce the amount of stress on the end mill. These end mills, we don't see really well because they rotate really fast, but when you're cutting, they have a little bit of deflection. Imagine a straw. A straw is a really thin object that bends a little bit on the side. Even if this is metal, this also happens. So in order to try to avoid this, we always try to enter by doing a soft slide on the material. We enter like in a slide. We don't do a vertical movement and then a lateral one. We will see this in the machine. Tool geometries. This is important on how you choose the machine, but there are two main factors that will constrain how you choose them. Benny, can you stop, please? So first is the cut length. This will determine the total depth of material you can cut. If your cut length is 20, it's recommended to only cut around 18 max of material. Why? Because if you are covering the material, this with the material, the material cannot escape, cannot get out. So you need to leave a little bit of space on to so you need to leave a little bit of space so the material can get out, the cutted material. We have the diameter. Usually, for the big milling machine, we use the same diameter in the cutting that in the shank. But some end mills can have, let me see, can be smaller. So you use the same collet, but you have a smaller cutting area. For example, the one that you are using for making PCBs, they look like this. They are really thin here, but they are thicker here, so they are stronger. And we have the flutes, the cutting knives, okay? A lot of people get confused. The flutes is the amount of cutting knives. How many edges we have? For example, here we have two, one coming in this direction. This one has two, one and two. We have two cutting knives. There are tools with 1, 2, 3, 4, 5, 6, 7, 8, 9, like that until 16, 32. I think I have seen until 48. So it's important the tool diameter that you use. It will constrain the minimum size that you can cut. When we cut, we are basically taking material out. We are rotating really high speed. We are cutting a little piece of material and we are pushing it out. For example, this end mill is a up cutter. It's pushing the material up. So it's a generalistic end mill. Some end mills, what they do is rotate, the blades are in the opposite direction, and they push the material down. You will say, you push the material down, there is no way to escape. Yes, on the back of the cut. So a down cutter always needs to cut in a line. That's why we cannot cut vertically, because the material cannot escape if there is no space on the back of the end mill. Okay, I will repeat that. Yes, it's important. So this end mill is taking the chip, as this color is not good, let's go with green, and pushing it up, no? Imagine that the tool geometry is the opposite, that is rotating like this. So when you cut, this piece is being pushed down. There is no space. So based on the rotation, it goes on the back, on the leftover space behind the end mill. It's pushing down and back, because the down cutter can only move on the side, cannot do just vertical plunges. It's quite important. Then we have different tips, all the different types, yes? It's next slide. The difference between different flutes is on the next slide. We have different tips. We have flat, round, and V-shapes or other geometries. The flat one can only produce flat cuts, of course. The round one will produce round cuts, and it's done for three-dimensional milling, and the V1 is for special carving. Let's see a little bit the differences. For example, if you produce cuts with round ones, you produce this bumpy effect. You will say, why you will want this kind of finishing? When you make a three-dimensional cut, like a slope, for example, what you do is you produce round cuts really close to each other. So if we look with a microscope, the surface is bumpy like this, but the bumps are really, really, really that small that we don't see them. So the round cut is to produce three-dimensional surfaces. The V cut is to produce, usually is meant to use engravings, like this, that you get a V shape. It's also used a lot when you have the edge of the material and you want that the material gets a 45 degrees or 30 degrees or 20 degrees angle cut. So you take the end mill, that is this part, and you destroy part of the material with a determinate shape. There are a lot of types of V cutters. There are like 90 degrees, 50 degrees, 30 degrees, and different shapes. There are even V cutters, or usually they are not called V cutters. Ooh, blue, let's take another color. That they, for example, sometimes they look like this. It's called special cutters. So what you will have is finally this end geometry. Okay? And you have a spoil bore cutters, for example. This is a big flat end mill that is used to flatten a lot of material at once. Basically, it's a big flat cutter. But when it becomes really, really big, it's called not anymore flat cutter, it's called a spoil bore cutter. What is a spoil bore cutter? Basically, is to cut the spoil board. What is the spoil board? The spoil board is the base of the machine. When we cut, we need to sometimes flatten the machine to make it flat again, because we need to replace it and we got some cuts. So we need to make it flat. For that, we use this end mill. There is only one rule for end mills in general. The bigger is better. Why? We can cut more material and faster. And this will be determined by the strength of your machine. Usually the machines have a maximum end mill size that you can mount. For example, for usually big machines, that size is around like 20 millimeters. A 20 millimeters end mill is a quite huge end mill. That means it can cut a lot of material at once. Why? The bigger is better. thicker and bigger in diameter, they are stronger. That means you can cut faster. You have seen, for example, the small milling machines cutting PCBs. We are going really slow. Why? Not because the machine cannot cut, because the end mill is really weak because it's really thin. So if it's really thin and you try to go fast, the end mill bends and breaks. Let's go a little bit, importance of chips. Okay. Flutes. Why we have 1, 2, 3, 4, 5, 6 flutes or more? The chips, what is the chip? The chip is how we call the piece that we cut it. Well, they are called chips because they look like potato chips. Exactly like that. They are small chips of material and they need to look like chip, not like dust. When you cut, you should not see dust. You should see chips. It's really important. These chips, they help with the heat transfer. That means this piece gets hot, and if it doesn't get hot, takes the heat of the end mill and take it out. So actually, the chips are both things. One is the cutted material, another one is working as a cooling material. So actually, the bigger the chips, the more heat that they can take, the easier it is to cut without having problems of fire or heat accumulation. In general, more flutes means better surface quality, but also that means more flutes is you need to cut faster. Why? Imagine that you are moving 1 millimeter with this end mill. You just produce a little cut. If you are moving 1 millimeter with this end mill, you are producing 1, 2, 3, 4, 6 cuts. So that means all the cuts, all the knives needs to have material. In order to have enough material to cool down, you need to cut faster. So that means more flutes, you need to cut faster. That means the speed settings are more difficult to set, but it's mandatory in order to have good cuts. So in general, if you want to have better surface finish, you want to use more flutes. If you want to have like slower finish, you want to use 1 flute. But also that increases with how difficult it is to set up the end mill. For example, 2 flutes end mill cuts more or less half the speed of a 3 flute end mill. What happens a lot is you have problems to attach your material properly. You have seen before that we have CNC machining centers that are very huge and bulky for a really small cut. Why? Because they are for professional use and they want to cut with high amount of flutes end mills, no? That means they need to cut really fast. They need to cut really fast. Usually they will have also problems of cooling. So they have water cooling or oil cooling, and also they need to clamp the material with a lot of strength so it doesn't move. Basically, we are cutting really, really fast. Usually, higher flute end mills are meant for like really professional applications when you want to have like the super nice, super finished quality, but that implies also a lot of technicality into the setup of the machine. In general, to don't overcomplicate, we use 1, 2, or 4 flutes. Like I have only used, for example, 32 flutes once, I think. For example, for small milling machines, as we cannot cut really fast because the end mills are small, we compensate by cutting with more flutes. So for example, for the small milling machines, you will see in molding and casting, we cut with 4 flutes. For the big one, to make things easier, we cut with 1 or 2 flutes. Less flutes means easier to cut also. But that doesn't mean that 1 flute has really bad quality. Actually, you can get super clean, smooth, finished quality with just 1 flute. It's all on the settings. So this is a little bit on conclusion on straight flute, up, down, and compression. A straight flute is generalistic one, is decent, not the best, not the fastest, not the slowest, but this is slightly difficult to find. Upcut is the best for chip removal. It means you will have less problems with heat, but it doesn't cut really well, for example, natural woods, because it tends to break the wood out. Downcut, really good for helping to hold your material into the bed, but you have a problem. You cannot make holes, and it's the slower to cut end mill. Compression is the best of up and down, is widely only used for composite application, and has a bad thing that is quite difficult to make the setups for this one, because we need to go fast but slow at the same time, depends on what type of cut you are doing. As I said before, like usually when you choose an end mill, you have data sheets with different sizes, different length on the cut length or the shank, etc. And we have some letters. For example, the one that you use for PCBs, they were aluminum titanium nitride coated. That is similar to ATI. Basically, it's to coatings to make the end mill last longer. When you see a goldy end mill, it's not because it's made out of gold, it's a like different coating material. And you have diamond ones that usually is for ceramics, composites or graphites. More flutes, smoother finish. Where flutes, they are easy to set up because they have less problems with heat. 1, 2, or 4 flutes are the most common ones. Fits and speeds. What are the settings that we use in CNC? In the CNC, we have 3 different settings. One is the chip load. And the chip load is an equation. And you said, for example, in the laser cut, you don't know, if you don't have a guideline of materials, you don't know how to start cutting, like what speed and power you need on the laser. In the CNC, it's easy. When you buy an end mill, they have a specific chip load. It means the total amount of material that this end mill can remove. And we have an equation. So an end mill usually has a chip load of, oh, what is this? No. Oh my God. Wait. Let's see. Oh my God. Okay. So when you buy an end mill, for example, it will state that this end mill for wood is 0.005. Okay. We want to know the feed rate, that is the speed that we want to cut. This is the incognita. And this is divided by the RPM and the number of flutes. We have chosen an end mill of, for example, 1 flute. I will draw it on the side, I think it's easier. Or just annotate into a, stop sharing, share whiteboard. So we have the equation that is chip load is the speed by the number of flutes by the RPM. So when you buy an end mill, it will tell you a range of numbers for the chip load. For example, chip load for plywood, this kind of end mill has a chip load of 0.005. This is incognita, it's the speed. We know the number of flutes, we have chosen the end mill, we are using 1 flute end mill, and what is the RPM? In general, what we want to cut as fast as we can, no? Like we want to use the maximum RPM of the motor. So let's put the RPM of the motor we want to use. We are cutting at 18,000 RPM. This is the revolutions of the machine that we are using. So what we do is we take out the incognita. What is the speed? 80,000 per 005. We are missing 10. Is 90. And this is the speed of cut. This equation, I'm sorry, only works in inch per minute. So 90 inches per minute means that we are cutting, we multiply 90 by 25.4, 1 inch is 25.4 millimeters. Where is the calculator? 90 per 25.4. We are cutting more or less as 2,300 millimeters per minute. We got an advance more or less of 2.3 meters per minute. This is the speed we need to cut. It's good because it seems a little bit annoying, but it's quite scientific. We have a value to start with. So even if you don't know how to cut a material, you can always go to the charts and check what are the recommended feet and speeds. The chip load is when you buy an end mill, it recommends you some chip loads. If not, you always find, for example, I'm sharing my screen. No. For example, you have chip load, plywood, usually 6 millimeter. You set up chip load charts. You can easily find it all over because they are quite the standard. So for example, if you use 1/8 inch end mill, always considering that it's a tough flute, for hardwood, you are between this range of chip loads. Why they say a range and not an exact number? Because depends, there are a lot of type of hardwoods. Plywood is not the same in summer that in winter. It could be a little more wet or more dry, so that changes a little bit. So you need to test the low and the high number, test a few lines of cut and see which one cuts better and get approximations. So always when you want to learn how to cut, what you do is you make some fit and speed test, the same as you do in the laser cut, to get to know which one is the correct value. But the good point is we have already a predefined average speeds that will more or less work, and it's a safe zone that you can stay on. So for example, for MDF, it's completely different from hardwood. You can see it's like quite faster than the other one. Why they don't specify the speed? Because we have something that is the RPM. Each machine has different RPM. So we cannot specify just one general RPM. So for example, the machine in the other building is from 10 to 70,000. This machine is from 18 to 24,000. So the range of RPM between different machines changes a lot. And then we have the cut depth. When we are cutting, we never cut at once. We cut a little bit, then we come down, we cut a little bit, and then we go down, and then we cut a little bit. So that means we cut in passes. In this case, it's really easy. You always cut less than half the size of the end mill. So if you are cutting with a 6 millimeter diameter end mill, you only cut half. It means 3 millimeter maximum. That's why bigger is better. If you cut with a 10 millimeter end mill, you cut 5 millimeter at once. You can cut more material and faster. And the step over is the side cut. Josep will explain this later on the Rhino Cam because it's easier to see. So for different materials, you have different chip loads. What happens if you cut too fast? or too slow. If you cut too fast, the machine cannot cut the material and will have problems to cut, and finally the end mill will break because it cannot cut that amount of material. If you are cutting too slow, there is not enough material, chips, to cool the end mill, and it will heat up and will destroy the end mill, or don't cut really well on your material, or make a fire, depends. There is a really easy rule to know if you are cutting well or not, and it's about noise. I always like to say that CNCs are like babies. If you are cutting too slow, the machine is not eating enough material, it doesn't have enough chips to eat, and it's complaining. So when the machine you are cutting too slow, the machine is crying for more material. So the machine makes like a noise, a really high pitch noise, because it's crying to eat more. If you are cutting too slow, the machine is having problems to eat the material. For example, what happens if you fill your mouth with hamburgers? Like, you go like that. So you make a really loud and deep noise. That means the machine cannot eat that amount of material you are cutting too fast. So always trust your ears. A CNC machine should make a stable, like average noise, like whoa. Sometimes it's easy to hear like whoa, whoa. Could be because the machine is turning on a corner. Like, I will say, don't laugh, because it's the best tip that I can give you. Trust your ears. It's really easy to hear if you are cutting well or not just by the ear. This we will explain in the station, conventional climb. What happens if you cut too fast? The machine cannot cut the material, so it breaks, or it can bend. What happens, for example, the machine can cut steel. Yes, but you have set up the values for wood. What happens, for example, if you try to cut the screw that you are using to hold the material? The end mill cannot cut the screw at that speed, so it will break or bend. So you will damage the end mill also. Be really careful by undercutting or by overcutting. One tip that we can do is we cut for 3 minutes, we stop the machine, and when the motor has stopped, we touch the end mill. You need to be able to touch the end mill with your fingers. If you cannot touch it because it's too hot or your fingers get burned, it means you are undercutting. It means you are cutting too slow. You will have heard that because you are cutting like, but even so, you can always check by the temperature of the end mill. Exactly, there is not enough material, the chip to cool down the end mill. Also, you can see on the chips that is on the size of the chips that is around here. This, the chips should look like a little like a pigtail in general, the small pigtails, or like mini potato chips. If you see dust, it means you are cutting your chips. It means you are not having enough material and you are cutting your cutted material. You are double cutting your cutted material. If you see dust, it means also you're cutting too slow. Be careful with the chips, sometimes especially with the metal ones, because they are basically cutting knives. Don't clean them with your hand. You will hit your hand to go to the hospital. And we just have 3 minutes more and we go to a break. So, best tips I can give you. CNCs are like a giant baby. If they scream, you are cutting bad. If they complain with a loud noise, you are cutting too much. You need to have a really round and stable noise. If you see smoke, obviously it's also bad. There is a fire. Keep it clean. It's important to have the dust collector on. The same as with the laser cut, we have the fume extractor. we are producing chips of material, so we need to take them out. Why? To help to cool down the material. If you have too much dust on the top of your material, that can lead also to a fire because it's accumulated material. There is no just one good value. Sometimes the values between different woods, the same material, changes a little bit just because this is about wood, water content of the wood. So one board is different. Wood is not an homogeneous material, it's heterogeneous. So that means different boards might have slightly different settings. So always trust a little bit the chip load, do some tests, and then cut. How to hold down the material? There are different techniques for different applications, but we try to simplify and just use one. One is the vacuum bed. It's the best one of the best ones, also one of the most expensive ones, and one of the easiest ones to break. Vacuum beds usually cost almost the same price of a machine, or half of it, depends on the machine. And basically they suck. It's a big vacuum cleaner sucking the material. It's really good because we don't need to have anything else to hold the material. It just sucks and holds it in place. What is bad is if you make a mistake, you can go through your material and cut your bed. I have seen a lot. Like all those vacuum beds I have seen so far, they have at least 1 or 2 cuts of mistakes. That means you are damaging basically a really, really expensive equipment. So usually this one you don't see a lot in a lot of educational schools. You see way more in professional environments because they take a little bit more care of the equipment. Even so, they are really good, but they have a problem. They are meant to work with large materials. If you put a really small material here, or like 3 by 3 centimeters, you cannot hold it in place. There is no enough surface to suck it. So usually these vacuum beds works with more or less medium to large size materials. Clamps. This technique uses the bed of the machine, the T-slots, to clamp your material. This is widely used when you're cutting really tough materials like metal, because you need to flex them really well. They have a constraint. That is, you cannot cut on the part that you're holding. So you have a lot of material wasted. We have screws. Good in general, you just screw the material to your bed. They have a bad point. You need to be really careful where you put your screws, so you don't go with the end mill on the screws. So it's important to know exactly where you have the screws on your bed. It's easy, it's cheap, and it is really forgiving. And we have double-side tape. In general, we try not to use this one, and we only use for foam. Foam is a really light material, and we don't need a lot of force to cut. So the foam usually holds really well with double-side tape. We don't recommend to other materials because if the material moves, it can lead to a serious accident. If foam moves a little bit, okay, it's not a big deal. But I know cases that, for example, they were cutting pieces of wax, hold it with tape. The wax, a big block, is around 2 kilos. The material got loose, start rotating on the end mill like a parabola, and then fly away, and basically went through the window, breaking the window. Luckily, it was the window and not someone's head. So you always try to use a safe hold down practice. When you cut your piece, happens the same in the laser cut. The piece gets loose, no? Can move freely on the material. In CNC, we use tabs. What basically does that mean is on the final part of the cut, we leave a little bit of material that we don't cut. What is that for? It's just to hold the piece in place so it doesn't fly away. This tab is really easy to cut with just a cutter knife. And we can do this also with aluminum. For example, with aluminum, the size of the tab is 0.5 millimeters. So that means it's really easy to cut. With wood, the size of the tab is 3 to 4 millimeters because 1 millimeter of wood is not strong enough. So usually we add these kind of connections onto our design to hold the piece in place. This we do it with a CAM software. We don't need to do it manually, okay? And on the bed of the machine is usually how it looks like. You have the bed of the machine, the aluminum T-slots, wood base of material, usually this is MDF, and your material. When you cut your material, you always cut a little bit more. Why? You want to be sure that you're cutting through your material. So if you need to cut 10 millimeters of wood, you cut 10.2. What happened? You are cutting more, so you are cutting the base of the machine. As we are cutting more, that's why we have the base wood material, so we don't damage the aluminum, because this is called the sacrificial board. It is a piece of material that needs to be replaced more or less yearly. Well, yearly, depends on the amount of use that you have, but here we do it more or less yearly. And when it's really used, it looks like this. You can see all the scratches, little cuts of the past cuts. Okay, safety reminders. This we will go on to the hands-on, but always, 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 always use safety glasses. Safety glasses are not this. This is not a safety glass. I will put you a video later on what the difference between a safety glass and a normal glass. It's not exactly the same at all. So always safety glasses. Always use ear protection. When we cut, we are producing usually a loud noise that is around like 80 to 90 or 100 decibels. To give you an idea, 90 decibels for more than 3 minutes, you start losing ear. So if you want to get completely lost your ear, it's up to you. But if you don't, use earpods protections. It's really important. And never, this is especially for summer, we are in Barcelona, next to the beach, you never use flip-flops in the lab, okay? Now it's winter, but in June, everybody will come in flip-flops. No flip-flop allowed on the machine. Read and know where the end stops are, like the mechanical end stops of the machine, the emergency push buttons. It's something that you don't need to be worried about using, like they are there for some use, and we use it at least once a month. In case something goes wrong, push it, the machine automatically shuts down. You lose your job, yes, but you don't produce a serious accident. Change to the sounds. So for example, sometimes we are cutting and we have cutting for like 2 hours, a really long cut, and it's ooh, and suddenly, ooh, yeah, something bad is happening. Like first, you should not be away from the machine. Second, stop the machine. The sounds give you a really clear idea of what is happening. Use the proper end mill and avoid unsafe hold-down practices. It means hold your material properly. One screw doesn't hold anything. You use at least 4 screws, one on each corner of the material, at least. And always air cut. This we will go in depth, Giuseppe, with how to use the machine properly. So how to break a CNC? If this slide exists, it's because I've seen this a lot. Moving over the machine limits. It means if the machine is 2 meters long, don't try to cut something that is 3 meters. The machine will try to go to the 3 meters position. And basically that means get out of the machine. Drilling the support. Be really careful when you set up the numbers. If you want to cut 50 millimeters, don't put 150. Sometimes you're in a hurry, you put the numbers, and you mismatch just one click. One click can mean an accident. So always double check all your numbers and settings. Breaking the cutter by cutting too fast or too slow. Forgetting to switch on the spindle. This depends on the machine, but some motors, you have to double check the action, the on procedure, so the machine doesn't start automatically. In this case, we don't have. And forgetting to fix properly. It means hold your material well. A lot of the problems comes because you didn't hold your material well to the best. That means the machine can move the material and it will fly away. I have seen machines lifting up 35 kilos with a 6 millimeter end mill. It means 35 kilos of wood in the air flying, 2 meters long. So be careful. They are really strong. It's a powerful equipment. But if you take down like proper workflows, you will never have an accident. Yeah. Sorry? Feed rate is the speed. Okay, this is about terminology. Horizontal speed is also called feed rate. In general, in CNC, horizontal speed is also feed rate. It's amount of feed of material that you're eating. Like, I don't know why, but they usually have like eating like terminology. Okay, let's go to the break, like really fast, 5-minute break, okay, bio break, and let's go split in two groups. So today, the stations are gonna be two groups. One, hands-on on the machine, how to put the material, how to make the cut and cut. We will do two sample tests of wood and plastic, and we will have another station in the Fab Academy room on how to make the file for the machine, okay? Okay, bio break.
You mean that one that has those bigger, it's similar to here, but it's not the same thing. You know, it has.
Okay. Aglomerado. Yeah, that wood is also not wood. Yeah, it's okay. You have natural woods, all kind, and natural woods can be processed.
A ver, porque esto...
Santi, mutea. Santi, mutea.
Echando así te la poso.
Santi, mutea.
Subida, y así tú hablas.
Yeah, it's a large tables. Yeah. Cut them. You notice it's not there. It's like wood chips, like
It's conglomerate board.
What is it? Sorry.
Conglomerate board. It's not OBS or OSB. You have OSB wood.
Yeah.
It's similar to this one, but in a small scale. No. All these can be milled. Actually, this one is a really underrated material. Cuts well, actually cuts well. What happened is it's not really structural. You mean this kind of wood, aglomerado, OBS, there are different qualities. That the really thin one, this one, is kind of a mix of OSB and MDF. Like the particles are bigger. This one cuts well. Yes, it cuts. The surface finish is not the best, but cuts well. It's cheap. And then IKEA, you have the composite board that is wood, cardboard core, and wood in the exterior. That is IKEA composite cardboard core. That is the lower, the cheapest furniture of IKEA, usually made like this. Yes. That's the difficult part. You need to make an average. You calculate for usually the toughest material. That is the one that it will break your end. And the other one, you always is complex actually. For example, happens the same with Alubond. Alucubond depends. Alucubond is a foam core material. It's aluminum, foam, aluminum. So in this case, you cut for the aluminum. You don't cut for the foam. But the point is here to cut the aluminum with a setting enough not to melt the foam core. It's a little bit out of the aluminum spectrum, but that depends on the type of end mill you choose or how fast you cut on the depth, etc. Yeah. That, for example, they call it the compression end mill. With compression end mill, if you want to actually Benny, the one that is the guy that's doing the furniture here, he's an ex-student. We hired to do some furniture because he likes to cut in the CNC and does it well. He used what is called the poor man compression cutter. That is, cuts the first part of the plywood with a down cutter, then changes to an up cutter to cut the second part of the wood. So this is a two-step process. You get the same finish as a compression, but you need to make two cuts. It's called the poor man compression cutter. Someone changing in the process. The problem with compression cutters is they are quite more technical because as you're cutting up and down at the same time, you need to cut your board at once. And that means your chip loads are completely different. The chip load equation only works when you cut half of the end mill diameter. If you can cut your material at once, actually, but the speeds and fits are completely different. And that you need to know. You need to know how to estimate. For example, if you cut more than half of the mill diameter, you can cut 3/4, the speed gets reduced around like 20%. If you cut full of the end mill, like 6x6, your speed gets reduced not 40, 30, and that changes. It's like, for example, when I want to cut fast, I want to cut at once. What I do is play with that number, but sometimes I calculate wrong and it breaks. I trust my ear, basically. I stay to the safe value, more than safe, and then I start speeding up as long as I hear a good sound. With plywood, what happened with use up cutter is the chipping of the top layer. That's why with plywood, we try to also use a down cutter to avoid the chipping. The chipping comes in the bottom layer, but as the bottom layer is pressed to the material, this is less prone to happen.
But then you said the down cut, like when, sorry, I look with we cut down, it can cut vertically.
Yeah, so you enter in a slide.
You're like,
Yes, I always enter in the slides, always, like no matter what tool I'm using. Like it's way better for the material and for the.
twice or how does it go? Later, so
What's one and becomes and destroys the ramps and go the next one. We'll see in the file. Plastics, they all cut awesomely. Like it's super amazing to cut plastic in general. If you're not getting a good cut, it's because your values are wrong. But no, it cuts really, really, really well. There are millions of plastics for different applications. It really depends. I cut acrylic. Acrylic cuts really well in the machine. It makes an awful noise to cut acrylic, but foam, there is a big difference on expanded and extruded polystyrene. Let's go for, yeah. Expanded is the one that are bubbles. Basically, imagine that this is a liquid that when they fabricate is in an oven, in a mold that is hot. Basically, they throw the material, the bubbles expand. That's why they are bubbles. The extruded is basically they push the material hot in from a like nozzle and expands all over. It doesn't formate bubbles. It's the same material, but the manufacturing process is completely different.
More dense.
It's also more dense because it's extruded. It's made by pressure. The other one is laid down and let it expand like foam, kind of. Expanded polystyrene cuts awfully. Extruded cuts really well. Really good for making molds. There are different kinds. The cheap way to use extruded polystyrene is go to a construction like site, like store, and buy the insulation foams from the walls. Like it's super, super cheap. There are different densities for different applications. Some of them resist better heat. For example, if you want to make semi-hot resistant molds, like not 200 degrees, but 100 something, you have like blue and heat resistant extruded. That is really good and it's tougher, even denser. Wax cuts really, really well and we'll use for making the molding and casting. You will get the really nice surface finish. For making molds, it's amazing and you can always reuse it because you can remelt down the wax. Okay, more materials. Scale, this is about different design. Scale, always 1:1. We always work in millimeters. Nest your material is really important. In nesting, we need to be careful of letting space between the parts. The same as the laser cutter, we can touch parts to each other. In the CNC, we cannot touch. We always need to leave a space between the parts. Let's see how. I will explain how, what, why later. Only vectors, CAM softwares. This is about designs. The only different rule is about the inside corner problem of the CNCs. With the laser cut, we are cutting with something that is a point. That point is around 0.25 millimeters. Basically, it's a round object, but it's so small that we don't see that it's round. What happened with the tool is we are rotating with a circular object that this has a diameter. In general, we use a standard of 6 millimeters. Or it's a good all-around worker. It's fast, but not too big. It's a good worker, like the 6 millimeter end. We have a problem that when you're cutting in line and you do inside corner, this is a circle because we are cutting with a circular tool. So how does you try, if you want to have this design, this is what finally happens. The mill produces this. To avoid this in joineries, we need to produce what is called dog bones, stick bones, or always like to call Mickey Mouses. that if you try to match the parts to each other, they don't fit. Why? Because this part cannot fit inside, gets stuck in here because the dimension changes. This joinery cannot sit completely onto this area. We have this area, and this is more prone to happen with bigger end mills. Bigger end mills, this problem gets bigger. What happened? We need to make some modification in the design. That is, do dog bones or T-bones. What we do is we make a path that creates this. So actually we get cutouts so we can match the parts one to each other. We have this that's called T-bone, and we have dog bone or T-bone aligned hidden in the seam. Actually, if you look closely to like the good furniture of IKEA, the ones that use plywood, they use a lot this technique. And what we do is they use smaller end mills and they try to hide these dog bones in some areas that you don't see. If you look, for example, someone that is not hidden in the cafeteria of IKEA, the clothes hanger that are trees, you can really, there are two simple pieces matches. It's difficult to hide it there. You can easily see the dog bones all over the parts. Actually, if you look at all this furniture, you will see all around that you have dog bones all over if you look close. The good point is we always try, we can hide them by using a smaller end mill. The dog bone is smaller. This will be like, if it's a 6 millimeter, the dog bone is a 3 millimeter. It's always half of it. If you use a 3 millimeter, 1.5. 1.5 is quite a small end mill. So this you have the point of hiding the dog bone, but taking more time in the cut or not doing it. There is one that is at 45 degrees angle that is more difficult to do. That is called, I call it the Mickey Mouse because it's actually like 45 degrees angle. It's something that you can take into approach. So there are ways to avoid that. That happens with straight angles. We have like soft shapes that are based on the round thing. You don't need to do dog bones because the end mill already gets, and actually you can see it here. This joinery is like that to avoid it. That is called the dovetail. Instead of making a connection like square, you make it round, and you don't need to do like dog bones. And this is there is a lot of joineries like this. You can, I will not go over right now because it's too much. There is a poster that is called the 50 digital joints. It's CNC safe wood joineries. I think already explained in the laser cut. You can download, they are in SolidWorks formats and DXF formats, and you can just use them as they are. And this is, for example, all kind of joinery that avoid the use of dog bones and is for interlocking parts in straight lines. And this is, for example, finger tenons. What happened, for example, if you have to add this is using a really huge end mill. For example, this is a 10 millimeter end mill as a minimum. This is what happened. Or for example, you can use them to hide them. The good point is we can control the total depth of cut, not like the laser cut. So you can only cut a little bit, leave like 2 millimeters of material and produce a hidden joinery. Actually, a lot of the speakers are made like that. They use hidden joineries. The good point is we can, as we can control also the locking, the depth, we can use locking joinery. It means it can be disassembled in one direction, but not in the other direction, because this little tab avoids that it gets out of the connection. Or we can use like double locking joineries that use a key, a master key, to lock the pieces in place. Joineries is something that is like huge thing. There are millions of types. This is the poster, like basically explains a little bit in short term. Like I have one printed at home, but it's nice in A1.
So you were saying before that there's fine with all the joints that we use?
Yes, just look for 50 digital joints, like with the second link or the first one in Google, just will go to, I think it's the library.
Yeah, but not the poster, yes, at
The DXFs.
okay.
I think I maybe have it restored, but I didn't find it in the hard drive. This is about joineries, how to use them, tolerances. Let's go. This is tutorials. In here, in the presentation, you will have 4 tutorials for 4 different programs. One is VCarve. VCarve is a nice tool. VCarve or ASPI is a nice tool. I use personally. We don't use it here because it needs license and it's super expensive, but it's like Illustrator for CNC. It has a nice interface in clear. In the house, not only here, but also in the other building, you always use RhinoCam. It's a plugin that you install into Rhino and it's good and it's really professional. But especially, this is completely personal. Especially, I'm not a really huge fan because I think it explains things in a slightly weird manner compared to other softwares. Maybe I'm just used to other softwares, etc. But it's a good tool and it's really powerful. It has, in fact, too many options for education, I would say. I think it was installed VCarve also in this computer, but we had to format it. It didn't work, so I will install it again also. VCarve tutorial, step by step. Then we have alternatives. FAM modules or mods also allows you to make CAM files. It's a really primitive CAM producer for CNC. Exists, I will not recommend. It's too big, honestly. This is how to produce CAM files with it. We have Meshcam. Meshcam is a freemium open source software. That means you can produce free files up to 500 lines of the code. It means you know what is a line of the code? The file you have produced in the scene, it was the 3D printers. For example, I think I have one of them here. Yeah, Benzi code, perfect. Benzi code. So basically, this is a file, and this is trash. But this is the instruction for the machine. This setups the speed, the acceleration, etc., etc., etc. So this software allows you to create 500 lines maximum. 500 lines is something not really complicated. But let's say if it's a simple design, you can do it. If you want to explore more lines, you need to pay like €3 of the license. It's a good software. It's a quite good software. That's why I recommend it. And for making small tests or just you want to try the tool, it's good. It works in Mac, PC, and also Linux. And it's really intuitive. It's graphic. That's something that in CAM softwares is not for CNCs. Usually they're not really graphic. It's a little bit technical. And they have different types of machine. Actually, it looks really similar to the software to produce CAM files for the SRMs. That is a dedicated software just for the rollers. We have Kanban that has also the same thing, 500 lines, and it's another alternative. And then we have RhinoCam, that is the one that we will use. We'll not follow this tutorial, we'll do it in live with you. But here is deeply explain everything. Actually, it's way more things explained that I will explain right now because today it's about learning how to make 2D and 2.5D files. In molding and casting, we will learn how to make 3D files because it changes completely the workflow. It's completely different. It's the same machine. You use the hardware setup is the same, but on the software side, it's completely different start. One you start with a 3D file, and the one you start with a 2D file. And then like match 3 controllers. For example, this is a standard machine software control. This when you go to like most of the machine CNCs, you rent a machine. Usually the software that it looks like in most of the machines. That is match 3. Match 3 is like the firmware control of most of the CNCs. It's quite complicated. It looks messy. There's too many options and buttons. The one that you use, I don't have it in the presentation because we bought it last year. I didn't have time to add it, but we have the video tutorial. That yeah. Santi Sendia is here, no? Computer control machining. Roland, yeah. Well, we just made the same as the other tutorial. This one also includes the parts of the software that In this case, it's slightly simpler. It's a similar interface, but with taking all the buttons that in general you never touch. Just have the basics. Having an accident or having problems with the CNC is not matter about complexity. It's about matter of being really methodic. We have like 12 steps. If you just miss one, everything is one. But like it doesn't admit any error or mistake. That is a big issue with the CNC. In the presentation, here we have set up like the rules, like the steps, step by step points, key points that you always need to check for producing the file. If you just miss one, everything will go wrong. And here we have a really, this one is 1 hour tutorial on just RhinoCam. Like we just shot it every year, and it's everybody gets to sleep while watching this video. But it's annoying if you want to get further, like RhinoCam, we can explain it in 5 minutes, or we can explain it in 20 days. It has so many options. That's why one of the things I don't like it too much, because it might seem a little bit confusing at the start for a fresh beginner. But it's a really powerful tool, on the other hand. Let's make a file. Today, one of the examples that we got with Giuseppe is this. We are going to produce this small passive speaker. It's a really silly thing. It's a piece of wood, like 3 layers of wood glued together to make us like passive speaker. You know how these guys work? Basically, they have a hole inside with a kind of parabola, and they augment the sound of your phone by the resonance of the wood. We already print sample files, and this is one of the examples of the practice. So let's go over the file. So we are in Rhino. How we open RhinoCam? Just type Rhino on the menu, on the command line. I just type it here, and it's suggesting me RhinoCam 2018. Okay, let's open it. Good. RhinoCam has a lot of options. I will just move this one to perspective. Okay. To be honest, I don't even know even a CNC software that produces good files. That is true. Not for Rhino, for anything like CNC post processors, or like they are not, like in general they cost from 3 to 15,000 euros. I think RhinoCam is 5K. Aspire is also 5K. In general, it's like standard price is 3 to 5K for post processors. CAMBAM and Meshcam are the closest, cheapest post processors that produce more or less good results. I have assembled a post processor in Grasshopper, but I'm not even showing you because you will get so scared. Like it's huge. But if you're interested, I can show you later. Well, you have the that's true. Sorry, I was completely wrong. You have the FreeCAD and Fusion. Fusion is good, but they have the problem that they are like standalone softwares. They are not free. You have embedded into other software like FreeCAD or Fusion. Fusion has a subtractive manufacturing and additive manufacturing tools in fabrication. The subtractive one haven't tried so far, but it's mainly specialized for 3D milling, not 2.5D milling, but it works. And the FreeCAD, I don't know, I haven't tried. Okay. So I would say that it's because usually these are kind of professional end machines. So the use set that you want some reliability. You don't want to you want the things to be really sturdy. For example, a lot of CNC machines, they don't use even USB connectors. They use parallel port serial, like the old printer one. Why? Because that one is way more reliable than a USB connector. You use their own dedicated computer. It's not a standard computer. The computer is embedded in the control box. With a CNC, you're working like with, let's say, big toys and serious toys. You want reliability at 100%. For example, just a main difference, the software that runs the 3D printer can run CNC. But it's not the same as like these small CNCs and these small CNCs. They use, this one is Marlin, this firmware that is a basic code for 3D printers, and this use GRBL. The difference on firmware is about reliability. These 3D printers, the firmware, at some point, like 0.0001% of cases, can lead to a failure. A failure in a 3D printer is not as catastrophic as in a CNC. Here, like, you are assuming that you need way more reliability and security on how it works, on how it accelerates, and how it moves. So the base code on the mechanic, from mechanics to firmware, is completely way more started in CNCs in general. Happen the same for the software. Like the slicers for 3D printed are millions, and sometimes happen. Like I've been using Cura since version 2, I think. They update, there is a bug, and suddenly that version doesn't work, or produce a bug or a glitch in some cases. A glitch in a 3D printer, you don't care. A glitch in a CNC usually means a broken end mill. And if you're cutting carbon fiber, a broken end mill at really high speed, something that you don't want that to happen. So in general, actually, that's one of the reasons why I think that most of the interfaces of CNC, they look like 90s style, because they don't update things. Like in general, for fabrication, if you don't update things unless you don't need, like it's the last thing you want to do. I have assembled a few CNCs, and some of them, they were running like the first generation of the firmware, and then we didn't want to update to the newer one just in case. And actually, happens that we updated, and the machine didn't stop working properly. Like 1 of 10 cuts was doing weird things. So we rolled down to the first generation of the firmware to make it work stable. To get an idea, for example, I know that case is Shopbot version 9.2. I know that in some machines, not all of them, that is super random. We assembled, we mounted the firmware, and the machine was moving. Imagine a machine like that, moving fast, and suddenly, like the full block that is 200 kilos with the motor on, jumping. The machine jumping, like it's heavy. That machine weighs like 600 kilos. Imagine the machine jumping. You don't want a machine like that jumping in your garage. Okay, so things to choose. First is we are in program. We have mill, turn. We are in milling. Turn is for lathe machine. This software also runs for lathe machine. We just choose the machine. We want a 3-axis machine. Just these things you need to check that they are correctly set up. We need the post processor. Post processor is quite important. Post processor is each machine, even if you use standard control, has different changes in the firmware. That means some of them, they don't interpret the G code in the same way. So we can make a file, but we need to export to the final format appropriate for the machine. Okay, so the file for that machine is slightly different that from this machine and for the SRAM. So that is where we choose the post processor. That is, choose the machine that you want to use. It's not the machine, it's the firmware that runs the machine. Usually the firmware that runs the machine is the same as the brand, because each brand makes its own firmware. And here, for example, we have all the types of CNC brands and firmware that exist.
Before we even start work.
Yes, you can change it later, but it's good flow to check first your basic settings and then make the file. For example, for this machine, we didn't have a processor. I had to write my own. I choose other examples, and I know, for example, it's not perfect. And in some cases, some really specific cases, it happens twice a year. It doesn't export well, and the machine gives you a warning. I'm just telling you, in that case, just like talk to me, and we will check what is happening. So in your case, the one that we are using is a CNC Steve DCM. If you get RhinoCam for your computers and you want to install this post processor, it's in my GitHub. Like you can download it. It's a file that you just put in the folder in edit. We just choose that one, and we don't need to touch anything. Then we choose the material. What material are we going to cut? Let's double click, and we need to set up. I don't know why, but it says the origin always in 0. We want to have the origin of the material in 0. Let's choose the maximum. A full board of material is usually not the ones that we are getting here, but in states like Korea, Japan, all over the world. In general, this is the standard full size dimension. 2440 by 1220. In here is about local manufacturers. They produce 2500 and 1250, like slightly different, slightly bigger. It's like the full board plus. We have the extra full board that is 3 by 2. Actually, that machine is not a full size, it's extra full size. It's 3.2 by 2.2. It's weird to find boots that big, but they exist. Let's put the thickness of the material. Always the same as the laser cut, we measure with the caliper in the different corners. I will say that as we are using the full size, usually measure in 6 areas, and you take the highest value. In general, I know that 15 is not 15, it's 15.5, 14.5. And it's really important to set up the Z on the top. The origin is on the top. Why? You are, I don't know if the camera is pointing to me or show video panel. Okay. So if this is the material and we have the end mill, we want to make the Z. The same as the PCB, you don't make the Z on the machine. You make the Z on the top of the material. So you need to choose that the Z is on the top. So the origin is on the X, Y, and Z top. So it's really important because by defect it's on the base. It's important to choose the top one. Okay, so now that we have it there, we can see the full size of the material. Okay, let's import our geometry. I have the file here, since it's speaker. I think it's speaker to the XF. Yeah. Import. Okay, let's erase this one. And to be sure, always, it's really important that your model is allocated flat. If your model is like this, the machine will still produce a cut. You have a problem that is higher, it will cut in the air. If it's lower, it will cut lower. It's really important to double check this.
What's the format of the file?
It's Rhino, whatever Rhino opens. Like this is a vector. Could be SVG to Rhino, or I use DXF because before I used to work with AutoCAD, and I produce a file with AutoCAD.
And you can do the same process for Fusion, if I go to something?
Fusion, I think so. Okay. I'm not completely sure. I think we have a Fusion tutorial on Medium, but okay. I need to find for it. I'll look for it. No, I'm really curious on using Fusion. I have the post processor for Fusion for this machine. I have it stored. Actually, as I didn't have the post processor of this guy, of this machine, this is a German machine. What I did is look in German forums for the post processor of Fusion for this machine. I opened up, I took a Rhino post processor and basically merged them together to create the Rhino version of this machine. The material?
Yeah.
The material, right now, it doesn't matter the material. This could be carbon fiber.
But it's always a board, right? Like,
Yeah, in this. Exactly. This is just, actually, this is a preview for you, for humans. This is not doing almost anything. It's just to give you a clear idea. So what I do is, I know that this file is flat. I locate in the origin, and now I move in a safe way. This is my personal workflow. Worked so far for like 9 years. I do a rectangle, also the same size as the material. Okay, I have the rectangle. It's just for a guideline for me. And I know I will put screws always in the corner. So I make an offset of 20 millimeters. In the area, I cannot place any object. Usually, I even leave a little bit more, 30 millimeters, because I know that I can easily put all the screws I want next to the corner. I will never have anything there. It's the safest hold down practice I can use. So we have this design. Let's move it here. And I will leave a space between my parts. I will measure the distance. The distance is 18 millimeters, more or less. So why I'm measuring this distance? I'm gonna cut outside. I'm gonna cut around here. So the end mill needs to have enough space to fit. What does that mean? If I make an offset, I'm gonna use a 6 millimeter end mill. Offset of 6 millimeter. This is actually what will happen. This is gonna be material destroyed. We need to leave a little bit of wood here. So actually this is not a lot of space. So I will leave a little bit more. So this piece of wood is stronger. And I will do the same here. But it's good, more or less. Exactly. If you want to save material, yes. Yes, if you use deep, it's called deep nest. Deep nest has a setting for it automatically. This is if you do like 3 files like this and you don't want to use deep nest. But if you go to settings here, a space between the parts right now is 2 millimeters. If I have 2 pieces, what is the space between the parts I want to leave? 6 plus 6 of the other part plus the space of wood that I want to keep. So it's 6 plus 6 is 12 plus 10. That depends on the material you use. 10 millimeters of wood is more or less strong. 5 millimeters is not really strong. So I will want to leave 22 millimeters of space between the parts. Why? Because if you cut and you only leave like 2 millimeters of wood, 2 millimeters of wood is really thin, it will break. For example, 2 millimeters of aluminum is way more than enough. Like, depends a lot on the material you use. Plastic, for example, acrylic, I will leave 5, but not less than 5. Why? Because it's brittle and the vibrations will make the acrylic break. Not because it's not strong, because the vibration of cutting, when we cut, we produce a lot of vibrations, it will make it break. Okay, we have the file, it's completely flat, it's perfect. We have different types of cut here. We have, I will show you with pictures. I think it's the easiest way. For example, here we have a pocket that is eat all the material. It different in stairs, no? So this is a pocket. It means cut all the material, but only certain amount. Let's go. We have this one, and this one. So in CNC, we always the same as the lecture. We go to the inside to the outside. In the CNC, is inside to outside and top to bottom. We will start from the top layers, the ones that cut less, to the ones that cut more, medium, the ones that cut to the bottom, and the same for the outside. So it's always pockets, then in cuts, and then out cuts. What is an in cut and what is an out cut? If we have this vector, we can cut with the end mill on the interior of the vector. We can cut on the exterior of the vector, or we can cut on the vector with the end mill aligned, end mill touching outside, end mill touching inside. This will give different results. In cut is when you want to have the exterior part of the dimension. Out cut is when you want to have the interior part. On cut is none of them. Is when you have design for on cut. In general, you don't design for on cut. Let's see. So let's choose this vector and let's produce what? A 2D axis cut. We are cutting in 2D. So right now, today is 2D cut only. It's called 2.5D, but it's 2D cut. We want to do a pocket that is cut all the material. Okay. We select the region, select curves. I have selected, I click enter, and it's selected. It's this one. Perfect. Then let's go to the tool. It's asking, okay, what tool are you going to use? In this case, we need to create the tool. In this computer, the tool are already saved. We just need to select them. If you don't have the tool, like this, the tools have numbers with the dimensions all over the tool. This is for example, is a ball. This is a flat end mill. This is wood. We're going to use a down cutter, one flute. It's one of the most generic tools we use here. Flat cutter, down. Down of up is not showing here. So I will name it flat millimeter, flat end mill, 6 millimeter. Holder diameter is 6. Holder length, I don't care. Shank diameter is 6. Tool length is 90. Tool diameter is 6. So it's an end mill that is straight. And has a cutting length of flute length. This one is 60, 27. This is the most important, the diameter and the flute length. That is the cutting area, that is the yellow part. Number of flutes, 1. And fits and speeds. This is where we have to set up the fits and speeds. And you see there is a lot of numbers to set up. Okay, what is the speed of the motor? This we use because we want to stay in the safe side. We use the lower one. We don't want to, we are not in a hurry. We set up 80,000 RPM. That is the smallest speed that we can go with the motor, this motor. And we have the cut speed. You see, I'm not touching these ones. I just touch cut speed. Cut speed is the horizontal cutting speed. I remember, I know this tool. I use it every day since like 4 years ago here. I know that the cut speed for that plywood that is class C is 5,000 millimeters per minute. And we start with this one, that is the cutting speed. This is the speed we want to cut. What? Hmm?
Is there any guide for this, or to know
The speed.
For each material? Or
The chip load equation.
it's the equation with but okay. But it means yeah, to do the how all these different okay, if you are using the material then maybe.
No. Actually, what the group assignment is find this value
Okay.
and do different tests at different speeds to see which one actually gets the better results. And in general, in wood, it's not the same cutting in this direction that cutting in this direction. So you need to test like angle lines, squares, and circles to actually get the average speed. To give you an idea, for example, this is a really annoying cardboard test. You see, it's a matrix of 80, 100, 120, 100, 6, 40,000, 10,000, 8,000 RPMs, changing to see which one gets the better cut with different tools. Basically, this is your group assignment. I don't know if I have more pictures. Yeah, for example, this is a chart, just changing 20 up, 20 down. This is in inches, not in millimeters. But for example, this is using a straight cutter, one flute, down cutter, one flute, range from 8,000 RPM to 6,000 for total 40,000 RPMs at feed rates of 60 to 120 inches per minute. Basically, you make charts, and these ones were the chosen one, and then another test with the final ones to see which one gets better. This is what you need to do for the group assignment.
If you want to create something like this,
Manually.
in Rhino, you have like a grid of squares, and then you need to set up a different tool, different speeds for each one of the squares, or it's something that you are changing on the program.
No, you do it here. In here, you have The same as in the laser cut, you have engraving, etc., etc. Here we have the same. In this scale, this is called toolpaths, because one style of cutting, second style of cutting, third style of cutting, and you can save all together later. So in here we choose cut. What is plunge, approach, engage, retract, departure? The name is states a little bit. So one thing is cutting, but to reach this direction, we need to first get down, then make a little turn, and then accelerate. So it's plunge, approach, engage, cut. Rule I use is 2/3 of the cut speed for all of them. Like in general, for woods, unless this aluminum changes, but is a little bit accelerating. It could be like more or less this plunge. If I'm in a hurry, 4,000. No, it's the first touch. Depends how you engage. Engage. There are two ways of engaging. That's later. And retract is get out of the material. This we are not cutting, so we can do the same. If you want to get, there is something that's called the CNC cookbook that is like, I think it's 1,000 pages for CNC machinists. They go really deep in this value. Like, no, it's at 30%. No, depends on the style of end mill, etc. This can get really complicated as much as you want, but you can also simplify a lot these values. Okay, we save as new tool. Okay, so we have the tool. Now let's go to fit. We can set up, we can change the speed and speeds here. It's the same values. We have already set up the fits in the tool. We don't need to change it anymore. We have clearance plane. What is the clearance plane? You see that we have this red line, red layer. When we are moving, cutting in one direction, we want to move up, move in the air, and go to another direction. It means what is the space we are leaving to move in the air? Clearance plane, like the safe height to move on the material. This, by defect, I always choose part sub mix plus 20. You can, in fact, you can go smaller movements, is shorter cutting times. Yes, but if the material is a little bit uneven, you can touch it. So I move up a lot and I move safe. Then we have the cut parameters. This is style of cut. You see, here we have the drawing. It's going to make one cut and then the other one. Or we have offset spirals, or linear, or spiral, radial, or high speed. Offset is the general one, works well. Unless your shape is a perfect cylinder, that in this case you want to use a spiral. It will save a little bit of time. This doesn't have a clear influence unless you are going really into data. Just usually has an influence on cutting time, and it's not huge. For this one, let's go to offset spiral. This is a cylinder, it's a circle, so it will cut well. And then we have cut climb or conventional. Okay, this is something really weird. Is type of cut. This is how you start cutting. It's the same, yeah. Conventional was the conventional, now climb is the conventional. So most of the cases you use climb. When the material is too soft or too hard, use conventional. Okay, that is the rule. Why? The motors before were weaker, so we didn't have enough strength to cut in climb. Climb needs more torque. Nowadays the motors are way more powerful, so we can cut with more strength. So we can use climb. What is the difference? Climb is this one. We cut a lot. It's like imagine yourself in the beach with a big spoon. What is easy? To take a little bit and dip hard and move it up, or take a lot and slowly take less? Exactly. So taking a lot and move it, like put the spoon completely inside and then take it out is more difficult than going softly, no? It's the same. It's exactly the same at really small scale. So you take a lot and you finish taking less. So it's like cutting hardly and sanding.
That's fine.
That's climb. This for aluminium, for example, you need a really strong machine, really sturdy machine. And for foam, what happened is foam is compressible. If you press a lot of foam, it compresses. So you don't get a good cut. With soft, really soft materials or really hard materials, you need to use conventional. That is, you take a little bit and you take a little bit more. In general, tomorrow we will go deep in this kind of things, okay? In general, climb, okay? Climb, that's it. And the step over distance is half of the tool diameter. When you know the rule, half of the diameter is always half of the diameter. If to be safe, it's 40%. And instead of 50, 40%. Cut levels. What is the total amount of cut we want? This is about the design, and this is with the wood we are using is 15 millimeters. I want to make 3 millimeters cut, 3 millimeters cut. So the total cut is 3.
I have a question about this part, because let's say that I have designed the speaker and I have the 3D model of the speaker. I know that there's a slope and whatever. So which is the best way to go from your nicely designed slope to deciding that you need 3 lines that go 3?
That is 3D model. We will go in modeling and casting because the approach is completely different.
Okay.
That is curved 3-dimensional cutting. Like it's.
So you really envision the speaker from the 3-dimensional, and then you think about cutting it like since that is design.
Exactly.
Okay.
How much we can cut? We are cutting 3 millimeter. We can cut 3 at once. It's one cut because we're using 6 millimeter ending. It's half of it. Okay. Pocket entry. We don't need to touch. Advanced parameters, going to touch. Sorting, we don't need to touch so far. Generate. You see, it's cutting. And here we can see, for example, the plunge, retract, engage, cut. This little ramp. So this is going to make the cut automatically. Now let's do the next one. That is this one. So this we always try to rename it. That is pocket 3 millimeter. Always try to put the names. You will have a lot of this path, and it can get really messy. I want to do is I have already set up everything. Let's duplicate this one. Copy. Let's go to copy. Thank you. Copy and paste it. They will open the second one. Remove everything. Select the next curve. Enter. I just checked that the values are okay. I take a deep look. Let's do it fast right now. I know it's going to be okay. The only thing that's going to change is how much we want to cut now. Now we want to cut 6 millimeters. So it's 6. What happened? The maximum cut we want is like cut 3 and then cut 3. We don't want to cut 6 at once. We need to do it in 2 steps. Generate. So now it's cutting 3 and 3. You can see that it's cutting the exterior and then it's duplicating the cut here. Okay. And then the final one that is cut completely through. We do the same. Copy. Duplicate. Remove.
Why do you want to duplicate that?
Wait.
And then you don't.
It's going to be time in the air, but you can avoid that area. They already cut it because you already cut it. What happens is if you don't do it properly, you can mess up things so fast. Like it's really easy to, I know what I mean. Why you don't start directly on the -3 step? You can do it. Tomorrow we will go on to that. But if you miscalculate a number, you can be finished cutting 9 millimeters at once. Like I see it every year. So it's better to spend 30 seconds more cutting in the air than have the probability to cut in the other way. Tomorrow we will go on to that. So let's just choose the last line. Okay, enter, and let's produce the cut level. We want to cut, in this case is 15 millimeters. Why? The material is 14.5. Let's add half millimeter more of overcut. 15. In this case, you see we need to move the slider to make steps of 1.5. It's usually multipliers of 3. It's okay again. Generate. It's generating. And it's cutting the first step, second step, third step, fourth step until it cuts all the material down. Okay, this is a pocket. Let's do an in cut or out cut. This one, we want to cut all the material here. Actually, I made a mistake. This is not good. I erased the older one. Distance 6. Offset. It was this one. I erased the internal one. No? Well, it's a test. It doesn't matter. This one, we want to cut and separate this part out. Let's do a profiling. Okay, let's select the curve we want to cut. Done. Okay. The tool, we already set up the tool properly. We check the speeds. The speeds are exactly the same. We just double check that they are okay. Clearance plane is exactly the same. It's plus 20 millimeters. It's safe. Like by defect, when you make the first setup, auto inherits the previous values. Cut parameters. We choose climb. And we want to cut inside. It means we want to cut here because we want to keep this area of material. So in this case, we need to say, hey, please cut inside. We need to activate. By defect, it will always cut on the line. So we need to activate. I want inside cut. Cut levels. We want to cut 15 millimeters. We want to cut through the material. And we need to do the same, the steps. 3 millimeters. Entry exit. Here is where it comes. Here we can really set up the slabs. We are cutting with a down cutter, no? We cannot do this movement. We need to enter it a slide. By defect, it does not the slide in the line. I will draw it, for example, but it will enter outside of the material, turn, and do a slide to enter cutting. This is good. What happened is it doesn't take into account other parts. What does that mean? If you have two parts close, the program is silly. RhinoCam, this is a feature that I don't like about RhinoCam. It can cut this part. Yeah, it's so silly. So the best way is enter on the projection of the line. Do a ramp on the same design. Let's see, for example, right now this is top view. Annotate, clear, all drawing. Top view, we use a long path. That is enter on the, do a slide on the line. Do you get that part? Yes? No? Tomorrow, I will go again on this, okay?
Question.
Yes.
Can you give an order for each box? Are you going to do each of them individually?
No, you can do have an order for each path.
Yes.
How you select the path manually will be the order.
In this case, I'm not sure I understand this correctly. You are trying to get along the path that you have selected in yellow because you want to empty a bit of material. So you want to go that.
Yes.
But also he's saying that if you want to set this up like this, and it's gonna dig into the material, so you come from the side and on the
Enters outside of the line.
yeah.
Right now we are entering in the line.
Is there no way to, for example, start in the middle of the path and then like you were drawing a spiral, for example, in the puppet? So is there a way to draw the spiral upwards, like from the center and then?
But right now we are not eating this part.
Okay.
That's why. So along path and exit none. It means exit vertical. Advanced cut parameters. We don't need sorting. This is layer ordering. For example, in the same in the laser, optimize to spend less time. We don't only have one line, so we don't need to spend less time. And we need to choose something. I forgot here. Advanced bridges. You remember we need to leave some areas of material that we don't cut to keep the part attached. In the moment we cut this will be a piece of wood free. We need to attach it somehow. We need to hold it in place. We're going to say, okay, we want rectangular tabs of 2 by 2, 2 by 4 millimeters. 2 millimeters height, 4 millimeters length. With a cutter knife, super easy to cut. And we want always 3 bridges, minimum. We generate. So now, for example, you see this here. You can see the slide is entering. It's a little slide. It's super subtle, but it's really important to have it. A slide going down, cutting one layer, and then moving another slide here, little bit. And this is the tab. That is the leftover part that we don't cut. And then this is the axis profiling. We need to do it. Not the first thing is after the pockets. And now we will do the exterior parts. That is this tree. Oops. What I can do is just choose this tree. Axis, profiling. It's exactly the same as we did right now. Everything is the same. Tool, we check the speeds. Clearance is already okay. Cut parameters. Here's what changes. Outside. We need to choose outside. We want to keep the part. Cut levels. Again, 15 millimeters. Steps of 3 millimeter. Entry, exit. Along path. None. Bridges. We want rectangular bridges. 3 bridges for each part. Sorting. You can say, okay, take the shortest order of cutting. Or none, it will choose the order I have selected the vectors. Generate, and it's doing it. You see, actually, he just put a bridge here. This is a really bad place to put a bridge. Like, I don't like this about RhinoCam. It tries to put the bridges always on the corners. How to avoid this? We can just go on the settings of bridges and distance between the bridges, or change to increase 2 or 4 bridges, change the amount of bridges, basically. So we have this. Let's put the last one. This is called outcut. Okay, and this is called incut. So first it will do pockets to the depth level, then the incut, and then the outcut. So now we have what is important, the simulation. Always, 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 always simulate your files. Always. Like, you can see almost all the mistakes in the simulation. So we just click simulate, play. We need to select something to simulate. Let's select everything.
These are all inside cuts, no? The ones that were inside, they're inside cuts.
Yeah, for example, this was the inside cut. We can see here it's inside the line. And the other one is the outside the line. And we can see the tabs here. Yes.
It's like the dent of the boxes in and that's if you rub it. If you want them to be straight, you have to change the path.
Look, but the part that I want is this one. It's straight.
Well,
It's the interior ones that are not straight. For example, here, you see, this we don't want, we don't have. In that case, we need to add the dog bone, the T-bone, and we need to do it manually. This is on the design. It needs to be in the vector. And that's the annoying part. So when you have this, it seems properly simulated. nothing is cutting more than the material, just a little bit, but not too much. This because we plan it. We can save this. How we do it? We right click and we can see the information. It's going to take 8.20 minutes, 8.20 seconds to cut. It's 8 minutes, 20 seconds, more or less. You always consider that add 20% more easily to these values. And what we do is post-process. That is save the file. 1, 2, 3. And it will open out automatically the G code. It's important. Why? Here, max depth cut 14.5 is telling you like important numbers, like what is the maximum depth cut, what is the tool that you have choose, because you need to put the tool that you have choose in the file. It's really important to check these two things: maximum depth of cut and tool you're using. And this is the G code, basically for the machine. That this one line number, I don't know how many lines we have, but this one is, for example, it's a simple file, but it's 1,500 lines of G code. We can simplify it a little bit to have less, but this is 1,000 lines. Yeah. Yeah. So the post processor, what it's doing is quite complex. So this movement, this in a G code, this is 1 point. This is another point. You can send this to the machine in a lot of different ways. We will have a make club about this. We can send this in a G1. We can send this in a G2. We can send this in a G3 type of G code, and each one is different. So this one we can divide this line into a lot of millions of points and go point by point, more lines of G code, different settings on the machine on the accelerations, or we can calculate this as a radius that in G code is E, J, with a start of the radius, start of the arc. So how you interpret the geometries is what the post processor does. How to interpret the movements. Is point to point is the same as the robots. Point to point, linear moves or arc moves. Yes, there are a lot of types of G codes and how you interpret. And for example, some machines, for example, this machine, M5 and M5 and M8 is the same command, but this machine doesn't read M5, only reads M8. So the processor does like final tweakings for your custom firmware of the machine, if you want to. You need the post processor for the machine you're using. You need the post processing for the machine you're using. You have the chance that your machine can read multiple types of post processors. Yes, but that's, for example, ¿Dónde está? Roland MDX 40. Okay, let's post process. Post. Look, same file for a different machine. Same file, eh? It's like different language. It uses the same alphabet, but different language. And each machine has different tweaks. Okay, I suppose you will have a lot of questions, no? Yeah. This is the easy one. This is 2.5D cutting. 3D cutting is way more complicated. Don't worry about this, you will get really used to. Like, it seems a lot, but in the fact is just knowing like where to touch in 10 boxes. And tomorrow we will go in deep in conventional climb style. Like we will go deep on the mechatronics on how what is happening at small scale. Because, for example, this sound is good. It's quite good, the sound actually. I was going to say like, no, this couldn't happen. No, it's quite good. But at some point we're cutting like this, and makes a little high noise at some points. Is, for example, in the corner, the speed is not enough because when the machine is getting to the corner, it decelerates to turn. So that means maybe the average speed is too low. We could increase a little bit, or we can take the corner in a different consideration. Or instead of cutting faster, we can cut deeper. There are little tweaks that you can always play to touch with the values. And these things you can define by the noise, like most of the times. Okay, as they're asking, yeah. I love the sounds. Thank you, Mayra. I don't know. Suppose you have like a lot of questions. Tomorrow the class will be like how to mill like a pro, if you want to call it like that. Well, actually, milling is one of my favorite tools. Like it's most professional. You can play a lot with it. For example, materials that you can or is difficult to cut. Carbon fiber, for example, you have a problem. Carbon fiber dust is really toxic for humans. It's really bad for lungs. So you can invent your. Usually, you need a HEPA filter to actually take the dust out. If you don't have a HEPA filter, that usually like it's quite expensive machine. What you can do is this is milling. Yeah. So for example, this is putting a water bucket on the top of the machine. So basically you're cutting inside water. So the dust keeps in the water. For example, this is a way to cut more or less safely carbon fiber. But this, for example, you cannot use an up cutter. You need to know that you can use up because it push ups. It will splash everything. You need to use a down cutter. In this case, you cannot cut the down cutter carbon fiber. You need to use a straight one so it doesn't stay. You need to use low RPM to compensate that, not make the water splash everywhere. This is, for example, cutting a little like drone frame. There are a lot of things and techniques and little tricks that you can use for milling. Okay, Mom, you're free. It's 2 already. We are really late today. Yoo-hoo!
Thank you.
I will see the other station, what is happening there. 1 second, guys. The remote screen. Guys, oh, I don't know if you are still there. The second stage was going to be hands-on on how to mount the endmills and everything. We will do it tomorrow morning. Even so, it's in the video that we just that Santi sends you.
It's also here. It's also here. They can look.
Se me ha pillado. Sí, se me ha pillado, ¿no?
Eso es que ¿te acuerdas que te pasó un día con el Zoom abierto?
Sí, sí.
Hay unas de FAP Academy de MDF que para el challenge quieren imprimir completo.
A los del.
Hey, Isabel, Kurt, Mayra, Tatiana, are you there? I cannot see you.
I'm here.
Okay. Can you see us? So just go to say bye. And so we have time to show you how to use the CSC. I think so tomorrow we will catch up. In the meantime, I think so, and it's going to be better than anything else. Yesterday I sent you the link to share video. I say you, and with all the talk of the lab, what of that? It's about how to use the sticker. Well, the steps for maintenance. I'm in my phone, so I cannot show you. But it's also in the documentation. The local documentation, there's I think so there's a section on the top that is guides, and then in the guides there's video tutorials of machines. It's also there. Wow. Type lines. Yeah.